In 1957, a group of astronomers working at the Tonantzintla Observatory in Mexico were conducting what seemed like routine work. They were photographing the night sky, systematically cataloging objects that appeared blue against the cosmic backdrop. This was painstaking labor, requiring special photographic plates sensitive to blue light, long exposure times, and meticulous record-keeping. Each night produced hundreds of images. Each image contained thousands of points of light. Most were ordinary stars in our own galaxy, unremarkable and expected. Among these thousands of blue points, one was logged as entry number 618 in the Tonantzintla catalogue. TON 618. It appeared as nothing more than a faint blue dot, indistinguishable from countless others. The astronomers noted its position, its apparent brightness, its color, then they moved on. There was no indication that they had just captured an image of one of the most massive objects in the observable universe. No hint that this tiny point of light represented something so extreme it would challenge our understanding of what nature can create. The catalogers could not have known. The theoretical framework needed to understand what they were seeing did not yet exist. Black holes were still mathematical curiosities, solutions to Einstein's equations that many physicists doubted were real. The concept of quasars had not been discovered. The universe's expansion and its implications for distance measurements were not yet fully appreciated. TON 618 sat in the archives, a mystery without anyone knowing there was a mystery to solve. The breakthrough that would eventually unlock TON 618's secrets came 6 years later, in 1963, when astronomer Martin Schmidt was studying an object designated 3C273. This object had been identified as a strong radio source, but when Schmidt examined its optical spectrum, he found something impossible. The spectral lines, the characteristic fingerprints of elements like hydrogen, were shifted dramatically toward longer, redder wavelengths, not just slightly, but enormously. At first, Schmidt thought the spectrograph was malfunctioning. The shifts were too large to make sense. Then the realization struck. These were ordinary hydrogen lines, but redshifted by cosmic expansion. The object was not nearby, but billions of light-years away. And if it was visible at such a distance, it had to be extraordinarily luminous, more luminous than entire galaxies containing hundreds of billions of stars. Yet it appeared as a point, suggesting all this energy came from a region no larger than our solar system. This was the first quasar, quasi-stellar radio source, star-like in appearance but with power beyond comprehension. The quasar revolution had begun. Astronomers realized these strange blue points were not stars at all, but the active cores of distant galaxies, powered by something far more energetic than nuclear fusion. Throughout the 1960s and 1970s, the picture clarified. Quasars were supermassive black holes, consuming enormous quantities of matter. As material spiraled inward through accretion disks, heating through friction before crossing the event horizon, it released vast amounts of energy, more energy per unit mass than any other natural process except the Big Bang itself. But TON 618 remained overlooked. One blue point among thousands in an old catalogue from a relatively small observatory. Decades passed. Technology improved. Telescopes grew larger. Detectors became more sensitive, replacing photographic plates with electronic sensors that could capture single photons with high efficiency. Spectrographs achieved higher resolution, allowing precise measurement of spectral line positions and widths. By the 1980s and 1990s, astronomers began systematic surveys of known quasars, measuring their properties in detail. When they finally turned their attention to TON-C ratio, analyzing its spectrum with modern instruments, the results were startling. The redshift was enormous, placing it over 10 billion light-years away. But more striking were the spectral lines themselves. They were extraordinarily broad, smeared out by Doppler effects from gas moving at tremendous velocities, thousands of kilometers per second. These broad lines indicated something massive at the center, something with gravitational pull strong enough to whip gas around at such extreme speeds. When astronomers applied the techniques developed for measuring black hole masses, using the relationship between line width and central mass, the calculations returned numbers that seemed wrong. Tens of billions of solar masses. They checked the math again, recalibrated the instruments, compared multiple independent measurements. The answer remained the same. This was not just a supermassive black hole. This was something in a class nearly by itself, an ultramassive black hole, containing 66 billion times the mass of our Sun. The distance presented its own revelation. Light from TON 618 has traveled for 10.8 billion years to reach us. When this light began its journey, Earth did not exist. The Sun had not yet formed. The Milky Way was still assembling from smaller protogalactic fragments. We are seeing TON 618 not as it is now, but as it existed when the universe was barely a quarter of its current age. We are looking backward through time itself, witnessing a cosmic monster from an era when galaxies were young and violent, when the universe was more energetic and chaotic than today. This time delay creates a strange disconnect. The object we observe, shining with the light of 140 trillion suns, showing vigorous accretion and active feeding, probably no longer exists in that state. Today, in real time, TON 618 has aged 10.8 billion years beyond what we see. It almost certainly sits dormant now, having long ago consumed the gas supplies that once fed it. The quasar has faded. The black hole, having eaten everything within reach, entered a quiescent phase that will likely last the rest of cosmic time. But we cannot see that future state. We can only see the past, frozen in the ancient photons reaching our telescopes. The quasar itself creates an observational challenge. When a supermassive black hole actively feeds, the accretion disk becomes extraordinarily luminous. For TON 618, the quasar outshines its entire host galaxy by factors of hundreds or thousands. This creates a problem similar to trying to photograph a candle flame while a searchlight shines directly into your lens. The overwhelming glare drowns out fainter details. The host galaxy, containing hundreds of billions of stars, becomes nearly invisible, lost in the quasar's brilliance. This is why understanding TON 618 took decades. Early observations saw only the bright point. They could measure its brightness, its color, its spectrum, but they could not resolve structure. They could not determine if this was truly a point source or an extended object whose details were simply too small to resolve at such extreme distance. Only with advanced techniques, observing at infrared wavelengths, where the quasar is less dominant, using adaptive optics to correct atmospheric distortion, could astronomers begin detecting the faint host galaxy surrounding the brilliant core. Even now, many basic questions remain unanswered. What does the host galaxy look like in detail? Is it a spiral like the Milky Way, or an elliptical like the massive galaxies found in galaxy clusters? Is it undergoing a merger with another galaxy, an interaction that might explain the vigorous feeding of the central black hole? What is the star formation rate? How much gas remains available for future accretion? These questions are difficult to answer when the central engine outshines everything else by such enormous factors. The discovery of TON 618 and the gradual realization of its true nature illustrates how science works. An observation made in 1957 only revealed its significance decades later, when theoretical understanding and observational capabilities caught up. The object was always there, its light traveling across billions of light years, but we lacked the context to understand what we were seeing. It required the quasar revolution of the 1960s, the development of black hole astrophysics in the 1970s and 80s, and improved instrumentation in the 1990s and beyond before we could finally appreciate what that faint blue dot in the Tonantzintler catalogue actually represented. This is the story of TON 618's discovery. Not a single eureka moment, but a gradual unveiling spanning decades. A mystery revealed layer by layer as human knowledge expanded and technology improved. And the story continues. New telescopes and new techniques promise deeper insights. Each observation adds detail to our understanding of this cosmic monster from the early universe. Numbers become meaningless at extremes. When we say TON 618 contains 66 billion solar masses, the human mind struggles to grasp what this actually means. We can write the number, we can perform calculations with it, but truly comprehending such magnitude requires anchoring it to familiar scales and building upward step by careful step. Start with Earth. Our planet contains roughly 6 times 10 kilograms of mass. Rock, metal, water, air, and life. Everything we have ever known, every human who ever lived, every structure ever built, all of it combined into this single sphere 12,742 kilometers in diameter. This is our reference point, the baseline of everyday experience. The Sun contains 333,000 times Earth's mass, approximately 2 times 10 kilograms. This already strains intuition. You could fit over 1 million Earths inside the Sun's volume. The Sun's mass dominates the solar system so completely that everything else, all the planets, moons, asteroids, and comets combined, represents less than 0.2% of the total. Jupiter, the largest planet, contains only about 1,000th of the Sun's mass. Earth is nearly insignificant, 3/millionths of the Sun's mass. Now multiply the Sun's mass by 66 billion. This is TON 618. If you could somehow place this black hole on a cosmic scale, with the Sun on the other side, you would need 66 billion suns to balance it. If you could line up suns, touching edge to edge, the chain would stretch for approximately 60 million light-years, the distance from here to the Virgo supercluster and back several times over. But black holes are defined not primarily by their mass, but by their event horizons, the boundaries beyond which nothing can escape. The event horizon radius is determined by a surprisingly simple formula from general relativity. For a non-rotating black hole, the Schwarzschild radius equals 2gm//2, where g is the gravitational constant, m is the mass, and c is light speed. This formula reveals something profound. The event horizon grows linearly with mass. Double the mass, double the radius. For the Sun, if you could somehow compress it down to become a black hole, the event horizon would have a radius of about 3 kilometers. The entire Sun's mass compressed into a sphere 6 kilometers across. For Earth, the event horizon would be roughly 9 millimeters, a marble containing our planet's entire mass. For TON 618, the calculation yields approximately 1,300 astronomical units. 1 astronomical unit, abbreviated AU, is the average distance from Earth to the Sun, about 150 million kilometers. This is a natural unit for measuring solar system distances. Mercury orbits at 0.39 AU, Venus at 0.72 AU, Earth at 1 AU by definition, Mars at 1.52 AU, Jupiter at 5.2 AU, Saturn at 9.5 AU, Uranus at 19.2 AUL, Neptune at 30 AUL, and Pluto, no longer classified as a planet, but still a useful landmark, orbits at approximately 39.5 AUL. TON 618's event horizon extends to 1,380 U. To visualize this, imagine placing this black hole where our Sun sits. The event horizon would extend far beyond all the planets, beyond Neptune, beyond Pluto, beyond the Kuiper Belt, where icy dwarf planets and comets orbit, beyond even the scattered disk, the region where the most distant known solar system objects orbit. the event horizon would reach approximately 40 times farther than Pluto's orbit. You could fit the entire solar system out to Pluto and far beyond, inside this black hole's event horizon, more than 30 times over. The circumference of the event horizon is even more staggering. Circumference equals 2 pi times radius, giving approximately 8,000 ATUs, or about 1.2 trillion kilometers. If you could somehow travel at light speed around this black hole's event horizon, the journey would take approximately 46 days. Light, moving at 300,000 kilometers per second, would need nearly 7 weeks for a complete circuit. For comparison, light travels from the Sun to Earth in about 8 minutes, from the Sun to Neptune in about 4 hours. Crossing the diameter of TON 618's event horizon would take light longer than it takes to cross our entire solar system hundreds of times over. These comparisons begin to convey the scale, but another approach helps. Consider mass density. Despite its enormous mass, TON 618's event horizon encloses such tremendous volume that the average density is surprisingly low. Volume of a sphere equals 4/3 pi r. For TON 618, this yields approximately 9 times 10 cubic meters. The mass is about 1.3 times 10 kilograms. Dividing mass by volume gives an average density of roughly 0.015 kilograms per cubic meter. This is less than the density of air at sea level on Earth, which is about 1.2 kilograms per cubic meter. The average density within TON 618's event horizon is less than 1/100th the density of the air we breathe. This seems paradoxical. How can something with the mass of 66 billion suns have lower density than air? The answer lies in the event horizon's definition. It is not a physical surface, but a geometric boundary in space-time. The actual matter of the black hole, according to classical general relativity, collapses to a singularity of infinite density at the center. The event horizon simply marks the radius within which escape becomes impossible. For more massive black holes, this boundary lies farther from the center. The volume grows as the cube of radius, while mass grows linearly, so average density decreases for more massive black holes. This has a remarkable consequence. For stellar mass black holes of a few solar masses, tidal forces at the event horizon are enormous, sufficient to tear apart any object instantly. But for ultramassive black holes like TON 618, tidal forces at the event horizon are relatively gentle enough that a human body could theoretically survive crossing the event horizon. The destructive tidal forces emerge only deep inside, during the final plunge toward the singularity. We will explore this phenomenon in detail later. To make the scale even more concrete, consider a thought experiment. Imagine we could construct a model where each millimeter represents one astronomical unit. On this scale, Earth's orbit around the Sun would be a circle 2 millimeters in diameter. You could draw it on paper with a pencil. Neptune's orbit would extend to 60 millimeters, about the width of 2 fingers. The event horizon of TON 618 would extend to 2.6 meters, roughly the height of a tall person. You would need a room to contain this model's event horizon. Or consider timescales. If we could somehow feed this black hole 1 Earth mass per second, a preposterous rate far beyond any realistic accretion scenario, it would take more than 3 million years to grow by just 1%. This black hole is so massive that even consuming entire planets every second would barely affect its total mass over human civilization timescales. The mass alone is one aspect of scale. The energy output is another. TON 618 shines with approximately 4 times 10 watts. This number means little until we anchor it. The Sun's luminosity is about 3.8 times 10 squared watts. TON 618 is therefore about 140 trillion times more luminous than the Sun. If you could replace the Sun with TON 618, maintaining the same distance of 1 AU from Earth, our planet would receive 140 trillion times more energy. The oceans would vaporize within seconds. The atmosphere would be stripped away within minutes. The surface would melt and then vaporize. Life would be sterilized completely within hours. Even from the galactic center, 26,000 light-years away, if TON 618 sat where Sagittarius A currently resides, it would outshine the full moon as seen from Earth. It would be visible during daylight, bright enough to cast shadows. The night sky would be dominated by this object, brighter than everything else combined except the sun itself. These comparisons use familiar objects, planets, the sun, distances we can name, to scaffold understanding of the incomprehensibly large. But even with these aids, the human mind struggles. We did not evolve to grasp such scales. Our brains developed to understand things we could see, touch, hunt, or flee from. Objects of human scale and timescales of human lifetimes. When we push to cosmic extremes, our intuitions fail. Mathematics carries us where intuition cannot. This is the scale of TON 618, a black hole so massive it makes our sun seem insignificant. So large, its event horizon could swallow our solar system many times over. So luminous, it outshines hundreds of billions of stars. A cosmic monster, defying everyday comprehension but yielding to mathematical description. An object teaching us that the universe creates structures far exceeding anything in our direct experience. Black holes span an enormous range of masses, from hypothetical microscopic quantum black holes that might exist for infinitesimal fractions of seconds to the ultramassive giants like TON 618. Understanding where different black holes fit in this spectrum requires a classification system based on mass and formation mechanism. At the smallest theoretical end are quantum or primordial black holes. These have never been detected and may not exist, but quantum mechanics and general relativity allow them. They could form in the extreme conditions of the very early universe, milliseconds after the Big Bang, when matter and energy densities were enormous. Any region with slightly higher density might collapse into a microscopic black hole. Such objects would have masses potentially ranging from a few micrograms to thousands of kilograms, with event horizons measured in subatomic scales. If they exist, they would evaporate almost instantly through Hawking radiation, vanishing before they could be observed. The smallest black holes we have reasonable expectation of detecting are stellar mass black holes, formed from the collapse of massive stars. Stars exist in a delicate balance between gravitational collapse pulling inward and pressure from nuclear fusion pushing outward. For most of a star's life, this balance holds. Hydrogen fuses to helium in the core, releasing energy that creates pressure supporting the star against its own gravity. But nuclear fusion has limits. When a massive star exhausts its fuel, the core can no longer generate pressure to resist gravity. For stars below about 20 solar masses, the core collapses into a neutron star, an object supported by neutron degeneracy pressure, where neutrons are packed so tightly that quantum mechanics prevents further compression. But for stars above approximately 20 to 25 solar masses, even neutron degeneracy pressure cannot halt the collapse. The core contracts without limit, forming a black hole. These stellar mass black holes typically range from about 5 to perhaps 100 solar masses, with most observations clustering between 5 and 20 solar masses. Their event horizons measure tens of kilometers in diameter, small by cosmic standards, but containing the mass of multiple suns compressed into regions smaller than cities. We detect stellar mass black holes primarily through their effects on companion stars in binary systems. As the black hole pulls material from its companion, the infalling matter heats up and emits X-rays before crossing the event horizon. These X-ray binaries create distinctive signatures. By measuring the orbital motion of the visible companion star, we can infer the mass of the unseen black hole using Kepler's laws of orbital mechanics. Between stellar mass and supermassive black holes lies a mysterious gap. Intermediate mass black holes, if they exist, would contain roughly 100 to 100,000 solar masses. Theoretical models suggest several formation mechanisms. Perhaps they form from runaway collisions in dense star clusters, where stars merge together repeatedly, building up mass until collapse creates a black hole more massive than any individual star could produce. Perhaps they are leftover seeds from the early universe that never grew into supermassive black holes. Perhaps they form through direct collapse of gas clouds under special conditions. Evidence for intermediate mass black holes remains uncertain. A few candidates exist, detected through gravitational waves from black hole mergers, or suggested by observations of bright X-ray sources in globular clusters and dwarf galaxies, but the population remains poorly characterized. We do not know how common they are or which formation mechanisms dominate. Then come supermassive black holes, the giants residing in the centers of most, possibly all, large galaxies. These contain millions to billions of solar masses. Their event horizons can span from fractions of an astronomical unit to hundreds of astronomical units. They cannot form from stellar collapse. No star is massive enough. Instead, they must grow through accretion of gas over time and mergers with other black holes when galaxies collide. Our own Milky Way harbors Sagittarius A, a supermassive black hole containing about 4 million solar masses. Its event horizon radius is approximately 12 million kilometers, about 17 times the Sun's radius, or roughly 0.08 HUA. Small compared to TON 618, but enormous by stellar standards. Sagittarius A is relatively quiet, accreting very little and producing modest radiation. Most of the time it sits dormant at our galaxy's center, making its presence known primarily through gravitational effects on nearby stars. Observations over decades have tracked stars orbiting Sagittarius A. One star, designated S2, completes an orbit every 16 years. At closest approach, it reaches speeds of about 3% of light speed, roughly 10,000 kilometers per second. By carefully measuring S2's orbit and applying Kepler's laws, astronomers determined the central mass with high precision. This provided some of the most direct evidence that supermassive black holes exist in galaxy centers. The supermassive category spans a huge range. At the low end are black holes of a few million solar masses in small galaxies. At the high end are objects of 10 billion solar masses or more in giant elliptical galaxies at the centers of galaxy clusters. The mass correlates strongly with host galaxy properties, particularly the stellar mass and velocity dispersion of the galactic bulge. More massive galaxies host more massive black holes. This correlation suggests that black holes and galaxies co-evolve, their growth intimately linked through shared gas supplies and feedback processes. Above the supermassive range, astronomers sometimes use the term ultramassive for black holes exceeding roughly 10 billion solar masses. This is not a precisely defined threshold, but a recognition that objects like TON 618 represent extreme outliers even among supermassive black holes, where typical supermassive black holes contain millions to low billions of solar masses. Ultramassive ones contain tens of billions. TON 618, at 66 billion solar masses, ranks among the very most massive known. Only a handful of comparable or possibly larger black holes have been identified, and all come with substantial measurement uncertainties. It is difficult to definitively rank them because different measurement techniques give different results with large error bars. But TON 618 is unquestionably in the top tier, representing perhaps the maximum mass that black holes can achieve given available time and growth mechanisms in our universe. Why does this category matter? Because formation and evolution mechanisms differ across the mass spectrum. Stellar mass black holes form from single stars in well-understood processes. Supermassive black holes require either massive seed formation, through processes we still debate, or extensive growth over billions of years through accretion and mergers. Ultramassive black holes like TON 618 push these growth mechanisms to their limits, requiring optimal conditions throughout their history. The mass categories also determine observational properties. Stellar mass black holes are detected primarily through X-ray emission from accretion in binary systems or through gravitational waves from mergers. Supermassive black holes are detected through effects on surrounding stars, gas, and radiation, and when actively feeding, they produce quasars visible across cosmic distances. Ultramassive black holes produce the most luminous quasars and the strongest gravitational wave signals when they merge, though such mergers are extremely rare. Understanding where TON 618 fits in this spectrum highlights its exceptional nature. This is not simply a large black hole. This is an extreme outlier, approaching theoretical limits on black hole mass. Its existence poses questions about early universe conditions, black hole growth rates, and the maximum structures gravity can assemble. Every measurement of TON 618 and its peers constrains theories of black hole formation and galaxy evolution. The classification system provides context. Stellar mass black holes are numerous, with hundreds of millions likely populating the Milky Way alone. Supermassive black holes are common, with essentially every large galaxy hosting one. But ultramassive black holes are rare. Only a few dozen candidates have been identified across billions of galaxies searched. They represent the extreme tail of the mass distribution, the largest gravitationally bound objects that nature creates. This rarity makes each example precious. Every ultramassive black hole discovered adds a data point to our understanding of what is possible. TON 618, as one of the most extreme examples, teaches us about the universe's capacity for building massive structures and the limits that physics imposes on growth. The journey from nothing to 66 billion solar masses requires understanding multiple pathways through which black holes form and grow. Number single mechanism can explain TON 618. Its existence demands combinations of processes operating over billions of years under favorable conditions. The most straightforward formation mechanism is stellar collapse. Massive stars, those containing more than approximately 20 to 25 solar masses at birth, end their lives in catastrophic collapse. After millions of years fusing hydrogen to helium and heavier elements in their cores, they exhaust their nuclear fuel. When the core can no longer generate pressure through fusion to support itself against gravity, collapse accelerates dramatically. Within seconds, the core contracts from thousands of kilometers in diameter to perhaps 50 kilometers. Densities exceed nuclear matter density, reaching levels where protons and electrons combine to form neutrons. For stars below about 25 solar masses, this creates neutron stars. But above this threshold, not even neutron degeneracy pressure can halt the collapse. The core continues contracting without limit, forming a black hole. The outer layers of the star, suddenly unsupported, fall inward, then rebound in a supernova explosion. The shockwave blasts outward, ejecting most of the star's mass into space. What remains is a black hole containing perhaps 5 to 100 solar masses, depending on the progenitor star's initial mass and how much was ejected rather than captured. This process produces stellar mass black holes efficiently. Every massive star becomes either a neutron star or black hole. Given that massive stars are common, with perhaps one forming for every 1,000 or so lower mass stars, stellar mass black holes should number in the hundreds of millions in a typical large galaxy. But stellar collapse cannot produce supermassive black holes directly. No star is massive enough. Even the most massive stars, theoretically possible, perhaps 200 to 300 solar masses, leave black holes below 100 solar masses. Getting from stellar mass seeds to 66 billion solar masses requires additional mechanisms. The first mechanism is accretion. Once a black hole exists, it can grow by consuming surrounding matter. Gas from nearby clouds or from companion stars in binary systems can spiral inward, crossing the event horizon and adding to the black hole's mass. This process is highly efficient at converting mass to energy, far more efficient than nuclear fusion, but still allows significant mass growth over time. Accretion is not unlimited. The Eddington limit imposes a constraint. As matter falls toward the black hole and heats up through friction in the accretion disk, it radiates energy. This radiation exerts pressure on infalling material, pushing it away. If accretion becomes too rapid, radiation pressure can overcome gravity and blow away the inflowing gas, shutting down further accretion. The Eddington limit for accretion rate depends on black hole mass. More massive black holes can accrete faster. For steady accretion at the Eddington rate, a black hole's mass grows exponentially with an E-folding time of approximately 50 million years. Starting from 100 solar masses, after 50 million years it reaches about 270 solar masses. After 500 million years, about 1 million solar masses. After 1 billion years, about 270 million solar masses. After 2 billion years, about 70 billion solar masses. This calculation suggests that growing a 66 billion solar mass black hole in the 3 billion years available before we observe TON 618 is mathematically possible with continuous Eddington limited accretion. However, this scenario is optimistic. Real black holes likely experience variable accretion, with periods of vigorous feeding interspersed with droughts when fuel runs low. Maintaining Eddington rates continuously for billions of years requires enormous, sustained gas supplies. This leads to the second question: where does the gas come from? Growing to 66 billion solar masses requires consuming hundreds of billions of solar masses of gas, even accounting for inefficiency where significant mass energy is radiated away rather than captured. This is a substantial fraction of an entire galaxy's total baryonic matter. Funneling such enormous quantities of gas into the central region over billions of years is non-trivial. Several mechanisms help. Galaxy mergers play crucial roles. When two galaxies collide and merge, gravitational interactions efficiently remove angular momentum from gas clouds, causing them to fall toward the newly merged galaxy's center. The merger event can trigger starbursts of intense star formation and simultaneously feed the central black holes. If both merging galaxies contain central black holes, these will eventually sink toward the center through dynamical friction and merge as well, adding their masses nearly instantaneously. The early universe was more conducive to such processes. Galaxies were smaller, more numerous, and closer together. Mergers were more frequent. Gas fractions were higher. Most baryonic matter was still in gaseous form, rather than locked in stars. This gas-rich, merger-active environment provided optimal conditions for rapid black hole growth. But even with favorable conditions, explaining ultramassive black holes at early cosmic epochs remains challenging. This leads to alternative seed formation mechanisms. Perhaps supermassive black holes did not start from stellar mass seeds at all, but formed through direct collapse of massive gas clouds. Direct collapse requires special conditions. Normally, gas clouds that become gravitationally unstable fragment into smaller pieces as they collapse. These fragments form stars rather than a single massive object. But if fragmentation can be suppressed, perhaps because the gas cannot cool efficiently, the entire cloud might collapse directly into a black hole. Theoretical models suggest this could occur in regions where intense ultraviolet radiation from nearby young galaxies photodissociates molecular hydrogen, the primary cooling agent for primordial gas. Without efficient cooling, the gas remains too hot to fragment, but can still collapse gravitationally. This process might create black holes containing 10,000 to 100,000 solar masses, or even more, providing massive seeds that give black holes a substantial head start. Evidence for direct collapse remains circumstantial. Observing such events directly is essentially impossible. They would occur at extreme distances in the very early universe and likely be obscured by surrounding gas. But if direct collapse produces massive seeds, it would significantly ease the challenge of growing ultramassive black holes in limited time. The third major growth mechanism is black hole mergers. When galaxies merge, their central black holes eventually merge as well, combining their masses nearly instantaneously in events releasing tremendous energy as gravitational waves. Each merger can double or triple the black hole mass in a single event, providing growth spurts far faster than possible through accretion alone. The challenge is getting black holes close enough to merge. When galaxies first collide, their central black holes are separated by hundreds of thousands of light-years. As the galaxies merge, dynamical friction from stars and gas gradually brings the black holes closer. But this process slows dramatically once the black holes reach separations of a few light-years. Further decay to the final in-spiral and merger requires additional mechanisms, possibly including interactions with stars or gas clouds that scatter away energy and angular momentum. Despite these challenges, mergers clearly occur. Gravitational wave detectors have now observed dozens of stellar mass black hole mergers, providing direct evidence for the process. Supermassive black hole mergers should also occur, though at lower rates. Future gravitational wave detectors like LISA will observe them directly, revealing the merger history of supermassive black holes across cosmic time. For TON 618 specifically, the formation and growth history likely involved all these mechanisms. Perhaps it started from a massive seed formed through direct collapse, providing tens of thousands of solar masses as an initial foundation. This seed then underwent sustained accretion, possibly sometimes exceeding Eddington rates during particularly intense feeding episodes. It likely experienced multiple major mergers as its host galaxy assembled through collisions with other gas-rich galaxies in the young universe. Each merger added mass, both from captured gas and from the merging of the other galaxy's central black hole. The exact sequence remains uncertain. Did TON 618 form as a single massive seed that grew steadily, or did it assemble through numerous mergers of smaller black holes, each themselves grown through accretion, or some combination? Current observations cannot definitively answer these questions, but the sheer mass achieved so early in cosmic history suggests favorable conditions throughout its history. Abundant gas supplies, frequent mergers, efficient accretion, a perfect storm of circumstances enabling rapid growth to ultramassive proportions. Understanding these formation and growth pathways has implications beyond TON 618. Every supermassive black hole in every galaxy grew through similar processes. The population of black holes across cosmic time constrains theories of structure formation, galaxy evolution, and the history of matter in the universe. TON 618, as an extreme outlier, pushes these theories to their limits and reveals where our understanding remains incomplete. Surrounding TON 618 extends a vast accretion disk, a swirling vortex of doomed matter spanning thousands of astronomical units. This disk is not simply a passive structure, but a dynamic, violent environment, where gravity, pressure, magnetic fields, and radiation interact in extreme conditions. Understanding the disk reveals how black holes convert mass to energy with efficiency unmatched by any other natural process. The disk begins far from the black hole, at distances where gravity's pull is relatively weak and temperatures remain cool by astrophysical standards. Here, thousands of astronomical units out, the disk resembles a slowly rotating gas cloud. Material might originate from stellar winds, supernova remnants, or gas captured during galaxy interactions. It orbits at a few hundred kilometers per second, comparable to planetary orbital velocities in our solar system. At these outer radii, The gas is mostly neutral, not yet ionized. Temperatures reach only a few thousand degrees, comparable to red dwarf star surfaces. The gas is relatively sparse, with densities far below Earth's atmosphere. If you could stand in the outer disk, you would perceive vacuum by human standards, with individual atoms separated by centimeters or meters. Yet compared to truly empty intergalactic space, this gas is relatively dense. As we move inward, following a parcel of gas as it gradually loses angular momentum and spirals toward the black hole, conditions intensify dramatically. Gravity strengthens. Orbital velocities increase according to Kepler's laws. At a few hundred astronomical units from the center, material orbits at thousands of kilometers per second, faster than the orbital velocity of innermost Mercury in our solar system. This increasing velocity creates shear. Inner material orbits faster than outer material. Faster regions rub against slower regions, and this friction converts ordered orbital kinetic energy into random thermal energy. Heat. The disk begins warming. Temperatures climb to hundreds of thousands of degrees. At such temperatures, atoms cannot remain neutral. Electrons gain enough energy to escape atomic binding, creating plasma, a state of matter where electrons and nuclei flow separately. This plasma conducts electricity and interacts strongly with magnetic fields. The interaction between moving charges and magnetic fields becomes crucial to disk structure and evolution. Magnetic fields are generated and amplified through dynamo processes. As plasma moves through weak seed magnetic fields, potentially left over from the interstellar medium or generated by turbulent motion, the motion of charged particles creates electric currents. These currents generate additional magnetic fields. Under the right conditions, this process runs away, exponentially amplifying weak seed fields into strong magnetic structures, threading the disk. These magnetic fields play multiple essential roles. First, they transport angular momentum outward through the disk. For material to spiral inward toward the black hole, it must lose angular momentum. Conservation of angular momentum would otherwise keep gas in stable orbits indefinitely. Viscous friction alone is insufficient. The disk would be too thin and friction too weak to transport angular momentum effectively. Magnetic fields provide an efficient transport mechanism through the magnetorotational instability. This instability, first understood in detail in the 1990s, causes weakly magnetized disks to develop turbulence that efficiently transfers angular momentum outward through magnetic stresses. Material connected by magnetic field lines to regions farther out effectively pulls that outer material forward, speeding it up and giving it more angular momentum, while the inner material slows down and loses angular momentum. This allows the inner material to spiral inward, while outer material moves outward. Second, magnetic fields create structure and variability. They tangle and twist, building up stored energy. Periodically, this energy releases through magnetic reconnection events, where oppositely directed field lines meet and annihilate, converting magnetic energy to particle kinetic energy and radiation. These reconnection events produce flares and variability in the disk's light output, causing the brightness to fluctuate on timescales from hours to months. As we continue inward, temperatures reach millions of degrees, then tens of millions, then hundreds of millions. The plasma glows intensely across all wavelengths. Visible light comes from regions at moderate temperatures, ultraviolet from hotter regions, X-rays from the hottest zones. This is why quasars shine across such broad electromagnetic spectra. Different disk regions at different temperatures emit radiation peaked at different wavelengths. In the innermost disk, within a few astronomical units of the black hole, conditions become truly extreme. Temperatures exceed billions of degrees, hotter than stellar cores, hotter than anything in nature except perhaps the first moments after the Big Bang, or the cores of merging neutron stars. Material moves at 30 to 50% of light speed. Relativistic effects become important. At these speeds, time dilation slows processes for the rapidly moving matter compared to distant observers. Length contraction distorts apparent dimensions. The black hole's rotation drags space-time itself, causing frame dragging where inertial reference frames are pulled around with the rotating black hole. This changes the structure of possible orbits. For a non-rotating black hole, the innermost stable circular orbit sits at 3 times the event horizon radius. For TON 618, this would be about 3,900 HUA. Material can orbit stably at this distance and beyond. Closer than this, orbits become unstable. The slightest perturbation sends material spiraling rapidly across the event horizon. For a rotating black hole, the innermost stable orbit shifts. If the black hole rotates rapidly in the same direction as the disk material orbits, the innermost stable orbit moves closer, potentially to just over 1 event horizon radius. If the black hole rotates oppositely to the disk, the innermost stable orbit moves farther out. Observations of disk emission can sometimes constrain black hole spin by determining where the innermost emission comes from. Material at the innermost stable circular orbit is on doom's edge. It has fallen through most of the gravitational potential well. It has reached maximum velocities and temperatures. It radiates energy at maximum rates. Any slight perturbation sends it past the point of no return, spiraling across the event horizon in what may be just hours or days of proper time for the infalling material, though appearing much longer to distant observers due to gravitational time dilation. This innermost region, though occupying only a tiny fraction of the disk's total volume, contributes disproportionately to the total luminosity. The energy release is concentrated where conditions are most extreme. This is why the most luminous emission comes from regions comparable in size to our solar system, despite the accretion disk extending thousands of times farther. The total energy output of TON 618's accretion disk is staggering, approximately 4 times 10 watts. For context, the Sun produces 3.8 times 10 squared watts. TON 618 radiates about 140 trillion times more. If you could capture even 1/1000th of TON 618's energy output, it would power human civilization at current rates for trillions of years. This enormous power arises from accretion's extraordinary efficiency at converting mass to energy. Einstein's E ratio mc squared tells us that mass and energy are equivalent, related by the speed of light squared. Even converting a tiny fraction of mass produces enormous energy. Nuclear fusion in stars converts about 0.7% of mass to energy when fusing hydrogen to helium. This efficiency allows stars to shine for billions of years. Black hole accretion achieves efficiencies of 10 to 40%, depending on black hole spin. For every kilogram of material crossing the event horizon, 100 to 400 grams are converted to energy and radiated away. This is 10 to 50 times more efficient than nuclear fusion. No natural process, except matter-antimatter annihilation, exceeds this efficiency. Current observations suggest TON 618 accretes approximately 20 to 30 solar masses per year. Every year, mass equivalent to 20 or 30 suns crosses the event horizon. With 10% efficiency, about 2 to 3 solar masses worth of energy radiates into space annually. This produces the observed luminosity. Despite this voracious appetite, the black hole grows slowly in percentage terms. Adding 30 solar masses per year to a 66 billion solar mass black hole represents a fractional increase of less than 1 part in 2 billion. Doubling the mass would take over 2 billion years at current rates. Even the most actively feeding quasars add only tiny percentages to their black holes annually. Extreme luminosity comes from efficiency, not from rapid mass growth. When astronomers first discovered quasars in the early 1960s, they were confronted with objects that seemed to violate known physics. These appeared as blue, star-like points of light, showing no structure even in the most powerful telescopes. Yet their spectra revealed something impossible. They were receding at velocities representing significant fractions of light speed, placing them billions of light-years away. At such distances, to be visible at all required luminosities exceeding entire galaxies containing hundreds of billions of stars. Yet all this energy emanated from regions no larger than our solar system. The name quasar comes from quasi-stellar radio source, reflecting their star-like appearance and strong radio emission. Though we now know that not all quasars are strong radio emitters, the name persisted. For several years after their discovery, the nature of quasars remained mysterious. Various exotic explanations were proposed. Perhaps they were not truly distant, but much closer objects ejected at high velocity from our galaxy. Perhaps they represented entirely new physics, unknown states of matter operating under unfamiliar principles. The answer, which crystallized through the late 1960s and 1970s, was both simpler and more profound. Quasars are supermassive black holes actively feeding on vast quantities of matter. The intense gravitational field near the event horizon provides the energy source. As material spirals inward through accretion disks, friction and magnetic interactions heat it to extreme temperatures. Before crossing the event horizon, this superheated matter radiates enormous amounts of energy across the electromagnetic spectrum. TON 618 is one of the brightest quasars ever discovered, shining with the luminosity of approximately 140 trillion suns. This extreme brightness arises from the combination of an ultramassive black hole and vigorous accretion. The black hole's enormous mass allows exceptionally high Eddington luminosity limits. When fed copiously, it can shine with intensities that would be impossible for smaller black holes without exceeding the Eddington limit and blowing away their fuel supply. To understand what makes a quasar bright, we must understand the relationship between accretion rate, black hole mass, and luminosity. The Eddington luminosity represents the maximum brightness a black hole can achieve through steady accretion without radiation pressure overwhelming gravity and shutting down infall. This limit scales directly with mass. A black hole 10 times more massive has 10 times higher Eddington luminosity. For TON 618, with 66 billion solar masses, the Eddington luminosity is approximately 5 times 10 watts. Observations suggest TON 618 shines at roughly 80% of Eddington, indicating very rapid accretion approaching the theoretical maximum sustainable rate. This places it among the most vigorously feeding black holes ever observed. The spectrum of quasar emission reveals the physical processes at work. At radio wavelengths, we detect synchrotron radiation from relativistic electrons spiraling in magnetic fields, potentially in jets launched from near the black hole. At infrared wavelengths, we see thermal emission from dust heated by the quasar's intense radiation, dust that may be distributed throughout the host galaxy. At optical and ultraviolet wavelengths, we detect emission from the accretion disk itself, with different temperatures corresponding to different radii. At X-ray and gamma-ray wavelengths, we observe emission from the hottest innermost disk regions and from high-energy processes like inverse Compton scattering. The emission lines in quasar spectra are particularly informative. Bright emission lines from hydrogen, oxygen, carbon, and other elements appear, created when intense ultraviolet and X-ray radiation from the central regions ionizes surrounding gas clouds. These clouds, collectively called the broad line region, orbit the black hole at distances of light days to light months from the center. Gas velocities in these clouds reach thousands of kilometers per second, revealed through Doppler broadening of the emission lines. By measuring line widths and time delays between variations in continuum emission and line emission through reverberation mapping techniques, astronomers determine both the size of the broad line region and the gas velocity. Combining these measurements through gravitational dynamics yields the central black hole mass. This is how astronomers measured TON 618's 66 billion solar mass. Quasars played crucial roles in understanding cosmic evolution. When astronomers catalogued quasars and measured their distances through redshifts, a clear pattern emerged. Nearby space contains very few quasars. The nearby universe, within a few billion light-years, is largely quasar-free. Most supermassive black holes today, including Sagittarius A at the Milky Way's center, are essentially dormant, accreting at tiny fractions of their maximum rates. But as we look farther away, looking back in cosmic time, quasars become more common. At redshifts corresponding to distances of 8 to 10 billion light-years, representing cosmic epochs 2 to 4 billion years after the Big Bang, quasar activity peaked. During this quasar era, bright quasars were perhaps 100 times more common than today. The universe was blazing with the light of vigorously feeding supermassive black holes. This evolution reveals cosmic history. In the early universe, conditions favored black hole growth. Galaxies were still forming, assembling from smaller fragments through mergers. Gas fractions were high. Most baryonic matter remained in gaseous hydrogen and helium, rather than being locked in stars. Galaxy mergers were frequent, as expansion had not yet carried galaxies far apart. These mergers efficiently funneled gas toward galactic centers, feeding central black holes and igniting quasars. As the universe aged, conditions changed. Gas was gradually consumed in star formation or expelled by supernova and stellar winds. Galaxy mergers became less frequent as cosmic expansion carried galaxies farther apart. Most massive galaxies completed assembly and settled into quiescent states. Without fresh gas supplies, black holes stopped accreting vigorously. Quasar activity declined dramatically. The quasars themselves contributed to this decline through feedback. As supermassive black holes feed and shine as quasars, their radiation heats surrounding gas. Intense ultraviolet and X-ray emission ionizes clouds and raises temperatures. Hot ionized gas has higher pressure and resists gravitational collapse. Heated strongly enough, gas can be blown out entirely in powerful winds, driven by radiation pressure and possibly by jets. This AGN feedback, active galactic nucleus feedback, regulates both star formation and black hole growth. As black holes feed and grow, their energy output increases. Eventually, feedback becomes strong enough to disrupt the gas supply, shutting down accretion. The quasar fades, the black hole stops growing. The galaxy settles into a quieter state. This self-regulation may explain why the most massive galaxies are not even larger. Without mechanisms shutting down star formation and black hole growth, theoretical models predict massive galaxies would continue growing to sizes far exceeding observations. The fact that we observe an upper envelope to galaxy masses and black hole masses suggests feedback limits growth. TON 618 exists at redshift 2.219, corresponding to when the universe was approximately 3.2 billion years old. This places it near the peak of the quasar era. We observe it during its glory days, when fuel was abundant and feeding voracious. The intense radiation we detect is both the product of this feeding and, ironically, probably the mechanism that will eventually end it. If we could observe TON 618 as it exists today, 10.8 billion years after the observed light left, we would almost certainly find something very different. The quasar has likely faded. The black hole may have grown somewhat, through continued accretion and possible mergers with other black holes during subsequent galaxy interactions. But it probably no longer shines near peak luminosity. It likely sits dormant at the center of a massive elliptical galaxy, a giant system containing trillions of ancient red stars formed billions of years ago during the galaxy's youth. The host galaxy has aged and quieted. Gas supplies have been exhausted through star formation, or expelled through supernova feedback and quasar-driven winds. The black hole, having consumed everything within reach, entered a quiescent phase that will likely last the remainder of cosmic time. Unless a major merger delivers fresh gas supplies, which becomes increasingly unlikely as expansion carries galaxies farther apart, TON 618's black hole will remain dark and dormant. This is the fate of most quasars. They shine brilliantly for a cosmically brief period, perhaps 10 to 100 million years, during and after major mergers when gas supplies are replenished. Then they fade, spending the vast majority of cosmic time in dormancy. We are fortunate to observe TON 618 during its active phase, catching a glimpse of processes that dominated the early universe, but are now rare. Quasars also serve as powerful cosmological tools. Their extreme brightness makes them visible across enormous distances, allowing us to probe conditions in the very early universe. Light, traveling from distant quasars, passes through intervening gas clouds and galaxies. This light carries absorption line signatures imprinted by gas along the line of sight, revealing the distribution and properties of matter billions of years ago. By analyzing absorption systems in quasar spectra, astronomers map how gas is distributed across cosmic time, how galaxies form and evolve, how heavy elements produced in stars enrich the intergalactic medium, and how cosmic expansion affects structure on large scales. Without quasars as bright background sources, much of this science would be impossible. TON 618, as one of the brightest quasars, serves particularly well as a cosmic lighthouse. Its light has traveled 10.8 billion years, passing through regions containing galaxies at various stages of evolution, gas clouds at various densities and temperatures, and cosmic structures spanning multiple epochs. Every absorption line in its spectrum tells part of cosmic history. The quasar phenomenon represents one of nature's most efficient energy conversion processes and one of the most powerful feedback mechanisms in galaxy evolution. Understanding quasars required combining general relativity, plasma physics, magnetohydrodynamics, radiative transfer, and observational astronomy. The story of quasar discovery and understanding stands as one of 20th century astronomy's great achievements, revealing that the universe creates objects more extreme than anyone imagined. The event horizon is perhaps the most conceptually challenging aspect of black holes. It is not a physical surface like the ground beneath our feet or the boundary of a planet's atmosphere. It is a mathematical surface in space-time, a boundary defined purely by geometry, yet its consequences are absolute. Cross the event horizon and return becomes impossible, forbidden not by lack of propulsion, but by the structure of space-time itself. To understand the event horizon, we must first understand how general relativity describes space-time. In everyday experience, space and time seem separate and independent. Space is three-dimensional, forward-back, left-right, up-down. Time flows uniformly from past to future. This separation seems obvious and fundamental. But Einstein's special relativity revealed that space and time are unified into four-dimensional space-time. What you perceive as space and what you perceive as time depends on your motion. Observers moving at different velocities disagree about the time interval between events and the spatial distance between them. What one observer calls purely time, another calls a mixture of time and space. Space and time are not separate, but intertwined. General relativity goes further. Space-time is not a fixed background, but a dynamic entity that curves in response to mass and energy. Mass tells space-time how to curve. Curved space-time tells mass how to move. What we call gravity is not a force pulling objects together, but the tendency of objects to follow straight paths, geodesics, through curved space-time. Near massive objects, space-time curves more strongly. Near extremely compact objects, like black holes, curvature becomes extreme. The event horizon marks a specific level of curvature where the geometry transitions fundamentally. For a non-rotating black hole, The Schwarzschild solution to Einstein's equations describes the space-time geometry. In these coordinates, the event horizon sits at the Schwarzschild radius, r_s equals 2gm//2. For Ton 618, this is approximately 1,300 astronomical units. This radius defines a spherical surface surrounding the black hole. Outside the event horizon, space-time is curved but not radically so. Light can escape to infinity, objects can orbit stably or fall inward but also turn around and escape if they have sufficient velocity. Time flows more slowly than far from the black hole due to gravitational time dilation, but it flows forward normally from the perspective of local observers. At the event horizon, something fundamental changes. The event horizon is a null surface, meaning light rays emitted tangentially to the surface remain on the surface, neither escaping outward nor falling inward. Light aimed even slightly inward falls toward the singularity. Light aimed even slightly outward also falls inward due to the extreme space-time curvature. Only light aimed precisely tangentially remains at constant radius. This reveals the horizon's nature. It is the boundary where escape velocity equals light speed. Outside, velocities below light speed can escape. At the horizon, even light speed cannot escape. Inside, escape becomes impossible regardless of velocity because all future directed paths point toward decreasing radius and ultimately toward the singularity. From the perspective of a distant observer watching an object fall toward the event horizon, something strange occurs. As the object approaches, it appears to slow down. Light from the object becomes increasingly shifted toward longer wavelengths and lower frequencies. The object grows dimmer and dimmer. It appears to freeze just above the horizon, fading to invisibility without ever quite crossing. This is gravitational time dilation taken to the extreme. Time passes more slowly in stronger gravitational fields. Near the event horizon, time dilation becomes infinite. An infinite amount of time for the distant observer corresponds to reaching the horizon for the falling object. From the distant observer's frame, the object never crosses, though it rapidly becomes undetectable as its light shifts beyond observable wavelengths. But from the perspective of the falling object itself, the experience is entirely different. Time passes normally. The object falls smoothly through space, accelerating as gravity strengthens. The event horizon, when reached, presents no physical obstacle. There is no barrier, no surface, no sudden change. The crossing is uneventful. The object continues falling inward, now irreversibly committed to reaching the singularity, but experiencing no local indication that anything special happened. This dichotomy, the distant observer sees the object freeze at the horizon, while the falling observer experiences smooth crossing, is not a contradiction, but a feature of relativity. Different observers, particularly those in different gravitational potentials or moving at different velocities, legitimately experience different time intervals between events. Both perspectives are valid in their own reference frames. After crossing the horizon, the falling object can still see the outside universe. Light from external sources falls inward freely, so photons continue reaching the infalling observer. Looking back toward the direction of entry, the observer would see the universe blue-shifted and time accelerated due to extreme gravitational effects. Potentially, the entire future history of the universe could play out in compressed time during the final moments before reaching the singularity, though this effect depends on specifics of the trajectory and space-time geometry. For Ton 618 specifically, the event horizon's immense scale creates surprising consequences. The tidal forces at the horizon, the differential gravitational pull between one's head and feet, scale inversely with black hole mass squared. More massive black holes have weaker tidal forces at their horizons. For stellar mass black holes of a few solar masses, tidal forces at the horizon are enormous, instantly fatal. But for TON 618, tidal forces at the horizon are relatively gentle, perhaps comparable to tidal forces experienced in low Earth orbit. This means a human body could theoretically survive crossing TON 618's event horizon. You would feel tidal stretching, certainly, an uncomfortable sensation of being pulled lengthwise and compressed from the sides. But the forces would not immediately exceed biological braking strength. You could cross the point of no return, still alive and intact. This is deeply counterintuitive. We imagine black hole horizons as places of instant destruction. For small black holes, this is accurate. But for ultramassive black holes, the horizon itself is survivable. The destruction comes later, deep inside during the final plunge toward the singularity, as tidal forces grow exponentially with decreasing distance. The event horizon also has a temperature, though for TON 618 this temperature is extraordinarily low. Hawking radiation, predicted by quantum mechanics, causes black holes to emit thermal radiation with a characteristic temperature inversely proportional to mass. For stellar mass black holes, Hawking temperatures are incredibly small, far below the cosmic microwave background. For TON 618, the Hawking temperature is approximately 10 Kelvin, just 1/4 of a degree above absolute zero. At this temperature, the black hole radiates negligibly. It absorbs far more energy from the cosmic microwave background than it emits through Hawking radiation. TON 618 is growing, not shrinking. Only in the far future, trillions of years from now when the universe has cooled below the Hawking temperature, will the black hole begin net evaporation. Complete evaporation would take approximately 10 years, a time span so vast that the current age of the universe is utterly negligible by comparison. The event horizon defines the black hole in a real sense. Everything about the black hole that can be measured from outside, its mass, charge, spin, is encoded in the horizon's properties. The horizon's area, for instance, is directly related to the black hole's entropy, the amount of information or disorder associated with the system. This connection between geometry and thermodynamics hints at deep relationships between gravity, quantum mechanics, and information theory, relationships still not fully understood. Inside the horizon, space-time geometry becomes even stranger. The Schwarzschild coordinates that work reasonably well outside become problematic inside. Better coordinate systems reveal that inside the horizon, the radial coordinate becomes time-like, and the time coordinate becomes space-like. This mathematical exchange reflects a physical reality. Movement towards smaller radius becomes as inevitable as movement toward future time is outside. You cannot stop falling toward the singularity any more than you can stop time from flowing forward. The singularity itself, at the center where all the black hole's mass theoretically concentrates, is not a place, but a moment. A moment in your future, inevitable and unavoidable once you cross the horizon. What happens at the singularity remains mysterious. General relativity predicts infinite curvature and density, but this prediction signals the theory's breakdown. A complete quantum theory of gravity is needed to describe physics at such extremes, and we do not yet have such a theory. For rotating black holes, described by the Kerr solution rather than Schwarzschild, the geometry is more complex. There are actually two horizons, an outer event horizon similar to the Schwarzschild case, and an inner Cauchy horizon where space-time becomes even more bizarre. The region between these horizons, the ergosphere, allows orbital motion where space-time itself rotates due to frame dragging. Processes like the Penrose mechanism and Blandford's Nagik mechanism can extract rotational energy from the ergosphere, potentially powering jets and adding to quasar luminosity. Whether TON 618's black hole rotates rapidly or slowly remains unknown. Measuring black hole spin requires detailed analysis of X-ray emission from the innermost accretion disk, observations at or beyond current instrumental limits for such distant objects. But theoretical expectations suggest rapid rotation is likely. Prolonged accretion from a disk naturally spins up black holes, with material carrying angular momentum inward. TON 618's long accretion history suggests it probably rotates at significant fraction of maximum spin. The event horizon represents a boundary in knowledge as much as in space. Beyond it lies a region permanently hidden from external observation. No information can escape. No signal can be sent out. What happens inside remains forever inaccessible to outside observers. This cosmic censorship is both frustrating and profound. The universe hides its most extreme physics behind event horizons, protecting us from seeing singularities directly, but also preventing complete understanding. Spaghettification. The term sounds whimsical, almost comical, but it describes a fate both fascinating and horrifying. The inevitable consequence of falling toward a region of extreme gravitational field. Your body stretched like pasta, pulled apart by differential gravity, until structure disintegrates completely. For TON 618, this fate is inevitable for anything crossing the event horizon, but the location and intensity differ dramatically from smaller black holes. To understand spaghettification, we must understand tidal forces. These arise whenever gravity varies across space. Earth's gravity pulls more strongly on your feet than on your head because your feet are slightly closer to Earth's center. The difference is tiny. You cannot feel it in normal circumstances, but it exists. This differential pull is a tidal force, named for how it creates ocean tides by pulling more strongly on the near side of Earth than the far side. Near black holes, tidal forces become extreme. Gravity strengthens dramatically as you approach. The difference in gravitational pull between your head and feet grows from negligible to noticeable to overwhelming to catastrophic. Eventually, the differential exceeds your body's structural strength. You are pulled apart. The mathematical description is straightforward. Tidal force is proportional to the mass of the central object divided by the cube of the distance. Closer proximity creates dramatically stronger tides. More massive objects create stronger tides at equivalent distances. But because the dependence goes as 1 over distance cubed, proximity matters more than mass for determining tidal force intensity. For a human body approximately 2 meters tall approaching a black hole, we can calculate the distance at which tidal forces exceed survival limits. Human tissue ruptures at stresses around 10 to 50 megapascals, comparable to the tensile strength of biological materials like bone and muscle. Using this threshold, we can determine when differential gravity across 2 meters produces forces exceeding structural integrity. For a stellar mass black hole of 10 solar masses, the fatal tidal force distance is approximately 400 kilometers from the center, well outside the event horizon, which sits at only about 30 kilometers. You would be torn apart before crossing the point of no return. The black hole kills you before trapping you. For Sagittarius A, the Milky Way's central black hole at 4 million solar masses, the event horizon sits at 12 million kilometers. Fatal tidal forces occur at roughly 8 million kilometers. Still outside the horizon, though much closer relative to the horizon radius, you would be stretched and killed just before crossing into inescapability. For TON 618, the calculation yields a startling result. With 66 billion solar masses and an event horizon at 1300 ATU, fatal tidal forces do not occur until you are well inside the event horizon. Perhaps 100 to 200 AUP inside, roughly 1,100 to 200 AUP from the center. You could cross the event horizon, fall inward for hours or days, and still remain alive and intact. Uncomfortable from the steadily increasing tidal stress, certainly, but not yet destroyed. This is one of black hole physics' deep ironies. The largest black holes are the gentlest at their horizons. Their event horizons are so large and gravitational field curvature so gentle that crossing is survivable. The destruction comes later, inevitably but not immediately. As you continue falling after crossing TON 618's event horizon, Tidal forces steadily intensify. The distance to the singularity decreases. The gravitational field strength grows. The differential across your body increases. Initially, you feel mild stretching, like being on a medieval rack, but gentle, uncomfortable, but bearable. As you fall deeper, the sensation intensifies. Your feet, closer to the singularity, are pulled significantly harder than your head. Your spine stretches, vertebrae separate slightly. Your arms and legs are compressed horizontally, squeezed from the sides as differential gravity in perpendicular directions manifests differently. You feel yourself becoming thinner and longer. Pain begins. Your tissues strain beyond comfortable limits. Blood vessels distend, organs shift position inside your body cavity. Bones stress under the differential pull. You are being deformed from a roughly cylindrical human shape into a longer, thinner configuration. Still recognizably human, perhaps, but distorted like a reflection in a funhouse mirror. Deeper still, forces exceed biological tolerances. Bones begin fracturing. Vertebrae separate and break. Muscles tear. Skin stretches beyond elasticity limits and begins rupturing. Blood vessels burst. Your body is coming apart, disintegrating from mechanical stress exceeding the strength of materials composing you. At some point, you lose consciousness, whether from pain, from loss of blood pressure to the brain, from pure trauma, awareness ceases, but the physics continues. Your body continues stretching. What was once a coherent human form becomes an elongated strand of tissue and bone fragments, still falling, still stretching, approaching spaghetti-like dimensions. Eventually, the forces exceed not just macroscopic structural limits, but microscopic ones. Cells are pulled apart, membranes rupture, organelles disintegrate. What was once living tissue becomes a suspension of molecules falling in a thin stream toward the singularity. Finally, even molecular bonds break. The electromagnetic forces holding atoms together in molecules are strong, but against sufficient tidal stress, even these yield. Carbon-carbon bonds, the backbone of organic molecules, rupture. Proteins, DNA, lipids, all the complex molecules of life disassemble into constituent atoms. Ultimately, you become a thin stream of individual atoms falling toward the singularity. Hydrogen, carbon, nitrogen, oxygen, phosphorus, and trace amounts of other elements. The atoms that once were you, organized into the staggering complexity of a living human being, are now simply falling debris. Individual particles in an inward-flowing rain. Even atoms might not be the final state. As you approach the singularity where space-time curvature becomes infinite, quantum effects we do not fully understand might come into play. Perhaps atomic nuclei are disrupted, breaking into individual protons and neutrons. Perhaps those nucleons are themselves torn into constituent quarks. Perhaps space-time itself ceases to be a meaningful concept, and physics as we know it simply stops applying. The timeline for this process depends on your trajectory and the black hole's specific properties. For TON 618, from crossing the event horizon to reaching the singularity might take many hours, possibly days of proper time, as measured by the infalling observer. This is dramatically longer than for stellar mass black holes, where the journey from horizon to singularity takes only milliseconds or seconds. The longer journey is a direct consequence of the black hole's size. Larger black holes have more space-time between the horizon and singularity. Light, traveling the same path, takes longer to make the journey. Infalling objects, accelerating under gravity but always remaining below light speed, take even longer. During this extended infall, you experience time normally. Hours feel like hours. Pain, if you remain conscious, persists for what seems like a long subjective duration. This is perhaps more terrifying than instant destruction. The process is drawn out, giving ample time for awareness of your fate before structure fails and consciousness ends. From an outside observer's perspective, you never reach this fate. They see you approach the horizon, slow down due to time dilation redshift, and fade to invisibility. To them, you appear to freeze just above the horizon. In their reference frame, an infinite time corresponds to your horizon crossing. They never see you spaghettified because they never see you cross the horizon, but your experience is different and ultimately more relevant. You do cross. You do fall inward. You do get stretched and torn apart. The process is real and inevitable in your reference frame, even if forever hidden from external observers. Tidal forces also affect large objects differently than small ones. A large spacecraft experiences tidal stress across its length, just as a human body does. But materials of construction, steel, aluminum, composites, have different structural strengths than biological tissue. A well-engineered spacecraft might survive somewhat closer to the singularity than a human body before rupturing. However, no material can resist tidal forces indefinitely as you approach a singularity. Eventually, forces exceed even the strongest chemical bonds. The strongest materials we know, like carbon nanotubes or graphene with extraordinary tensile strength, would still eventually yield. The progression would be the same. Elastic deformation, plastic deformation, structural failure, disintegration into constituents, just at smaller distances. Interestingly, tidal forces create one possible observable consequence outside the event horizon. If a star passes too close to a black hole, tidal forces can tear the star apart in what's called a tidal disruption event. These events produce characteristic X-ray and optical flares, as stellar material is stretched into long streams, partially captured by the black hole and partially flung away at high velocity. Astronomers have observed dozens of such events, providing evidence for supermassive black holes in galactic centers and testing models of tidal physics in extreme gravity. For TON 618, any star passing within several hundred ATU might be tidally disrupted. Given the enormous size of this danger zone, any stars in the vicinity have likely already been consumed or disrupted. The region immediately around the black hole is probably swept relatively clean of stars, leaving only the accretion disk material as the primary infalling matter. Spaghettification reminds us that black holes are not merely exotic astronomical curiosities, but represent extreme physical conditions where familiar concepts like structural integrity and body coherence simply cease to apply. No material can resist. No force can prevent it. Once inside the horizon, disintegration is inevitable, written into the geometry of space-time itself. Many actively accreting black holes, including possibly TON 618, produce one of the universe's most spectacular phenomena, relativistic jets. Narrow beams of matter and energy launched from regions near the black hole's poles, shooting outward at velocities approaching light speed, extending thousands or even millions of light years into space. These jets represent efficient mechanisms for extracting energy from black hole systems and play crucial roles in shaping galactic environments. The exact process producing jets remains debated, but the leading theoretical framework involves magnetic fields threading the accretion disk and potentially the black hole's ergosphere. As the disk rotates and the black hole spins, magnetic field lines anchored in conducting plasma become twisted and helical. This twisted field configuration can accelerate charged particles to enormous velocities and focus them into narrow collimated beams perpendicular to the disk plane. Two main mechanisms likely contribute. The Blandford-Payne mechanism extracts energy from the rotating accretion disk itself. Magnetic field lines rooted in the disk wind up as the disk rotates, creating helical field structures. Plasma flowing along these field lines is accelerated outward and collimated by magnetic pressure, forming jets. The energy source is the disk's rotational kinetic energy and gravitational potential energy, extracted as material spirals inward. The Blandford's-Narjek mechanism extracts energy directly from a rotating black hole. Frame dragging in the ergosphere causes spacetime itself to rotate, dragging magnetic field lines anchored in the surrounding plasma. This rotation of field lines can drive electric currents and power jets, extracting the black hole's rotational energy. For rapidly spinning black holes, this process can be extraordinarily efficient, potentially tapping the enormous energy reservoir locked in the black hole's spin. The relative contributions of these mechanisms depend on accretion rate, magnetic field strength, and black hole spin. For some systems, disk-powered jets dominate. For others, spin-powered extraction contributes significantly. In general, the most powerful jets likely involve both processes working in concert. Observationally, jets manifest across the electromagnetic spectrum. At radio wavelengths, synchrotron radiation from relativistic electrons spiraling in jet magnetic fields creates extended radio structures. Radio galaxies show jets reaching hundreds of thousands to millions of light-years from their central black holes, far larger than the visible galaxies themselves. These jets terminate in enormous lobes of radio-emitting plasma, carved out where the jet plows into the intergalactic medium. The jets from TON 618, if they exist, not all quasars produce prominent jets, would be among the most powerful in the universe. Given the black hole's extreme mass and luminosity, any jets would carry tremendous energy, potentially affecting galaxy evolution over vast regions. Jets achieve remarkable velocities. Observations of radio jets in various active galactic nuclei reveal apparent superluminal motion, where features in the jets appear to move across the sky faster than light speed. This is not true faster than light travel, which relativity forbids, but a projection effect. When a jet moves toward us at close to light speed, the light emitted by features moving along the jet arrives at Earth with progressively shorter time delays. This compression of arrival times makes features appear to traverse angular distances on the sky in less time than light would take, creating the illusion of superluminal motion. By measuring this apparent speed and accounting for projection effects, astronomers determine true jet velocities. Many jets move at 90% to 99% of light speed. Some features might reach even higher velocities, perhaps 99.9% or more. At such speeds, relativistic effects dominate. Time dilation slows processes in the jet's rest frame. Length contraction compresses distances along the motion direction. The relativistic Doppler effect dramatically amplifies emission from matter moving toward us, while suppressing emission from matter moving away. This creates relativistic beaming, where jets pointed toward Earth appear far brighter than jets oriented away from us, or perpendicular to our line of sight. A quasar, with a jet pointed directly at us, might appear hundreds or thousands of times brighter than an identical quasar oriented differently. This orientation dependence complicates population studies, as observed properties depend not just on intrinsic characteristics, but on viewing angle. The power carried by jets can be staggering. The most powerful radio galaxies produce jets carrying 10 to 10 ergs per second, equivalent to roughly 10 to 10 watts. This is comparable to, or exceeding the electromagnetic luminosity from the accretion disk itself. In such systems, jets carry away more energy than the disk radiates, making them the dominant energy output channel. For TON 618, if jets exist and carry even 1% of the total energy budget, they would transport approximately 4 times 10 watts. This is still billions of times the sun's luminosity. Such jets would have profound effects on surroundings, heating gas, driving shocks, creating enormous cavities in the intergalactic medium. The impact of jets on galaxy evolution is significant. Jets deposit mechanical energy into the surrounding gas, heating it and preventing cooling. Without jets and other AGN feedback mechanisms, theoretical models predict that gas in massive galaxies would cool efficiently and rain down toward galactic centers, fueling continuous star formation. Galaxies would continue forming stars at high rates and grow much larger than observed. Jets prevent this by injecting energy that maintains high gas temperatures. Hot gas has high pressure and resists gravitational collapse. Star formation is suppressed. Galaxy growth is regulated. This AGN feedback through jets is thought to be a crucial mechanism explaining why the most massive galaxies are not more massive and why they are largely quiescent with little ongoing star formation. Observational evidence supports this picture. Radio observations of nearby giant elliptical galaxies at the centers of galaxy clusters often reveal enormous cavities in the hot X-ray-emitting intracluster gas. These cavities, sometimes called radio bubbles, are carved by jets pushing aside the ambient medium. The volume of these cavities, multiplied by the surrounding gas pressure, gives the energy required to inflate them. Calculations show these energies are enormous, requiring sustained jet power over millions of years. The magnetic fields in jets are crucial to their structure and emission. These fields are likely generated in the disk and carried along with the outflowing plasma. Field strength in jets might reach milligauss to Gauss levels, enormously stronger than the micro-Gauss fields in interstellar space, but weak compared to fields in neutron stars. These fields confine and collimate the jets, preventing them from dispersing. Magnetic pressure pinches the jet inward, maintaining narrow beams over vast distances. Without magnetic confinement, thermal and ram pressure would cause jets to expand and dissipate rapidly. The stability of observed jets over thousands or millions of light-years requires strong magnetic fields. Particle acceleration in jets remains an active research area. Somehow, jets accelerate electrons to ultra-relativistic energies, giving them Lorentz factors potentially exceeding 10 or 10, meaning they move at 0.99999 plus times light speed. These energetic electrons produce the observed synchrotron radiation and inverse Compton emission. Several acceleration mechanisms have been proposed. Shock waves, where the jet collides with slower-moving material, can accelerate particles through first-order Fermi acceleration. Magnetic reconnection events, where twisted field lines break and reconnect, can convert magnetic energy to particle kinetic energy. Shear layers at jet boundaries might generate turbulence that accelerates particles. Likely, multiple mechanisms operate simultaneously in different jet regions. The composition of jets, whether they consist primarily of electrons and positrons, electron-proton plasma, or some mixture, remains uncertain. Different compositions produce similar electromagnetic signatures, making them difficult to distinguish observationally. Detecting high-energy neutrinos from jets would indicate proton acceleration and could help resolve this question. So far, evidence is limited, with only a few tentative associations between neutrino detections and active galactic nuclei. For TON 618 specifically, whether it produces prominent jets remains observationally uncertain. Some quasars are strong radio emitters with clear jet signatures. Others are radio quiet, with no detected jets or only weak jet features. TON 618 was catalogued originally as a blue stellar object, not selected as a radio source, suggesting it might be radio quiet or only moderately radio loud. However, detection limits matter. Even weak jets from a quasar at 10+ billion light-years distance might be difficult to detect with current instruments. More sensitive radio observations could potentially reveal jet structures currently below detection thresholds. Future instruments like the Square Kilometre Array will have sensitivity orders of magnitude better than current radio telescopes, potentially detecting jets from distant quasars not previously known to have them. If jets exist around TON 600, they would extend across cosmological distances. A jet operating for even 10 million years, a relatively brief time compared to quasar lifetimes, transporting matter at 99% light speed, would reach nearly 10 million light-years in length. Across such distances, the jet would impact enormous volumes of space, potentially affecting star formation in multiple galaxies, heating intergalactic gas, and enriching the cosmic web with energy and potentially heavy elements synthesized in the host galaxy and ejected through the jet. Jets represent one way black holes couple to their environments, on scales vastly exceeding the black hole itself. An object with event horizon measuring 1,380 Us affects its surroundings out to millions of light-years. The ratio of scales is staggering. The black hole is trillions of times smaller than the region it influences. This multi-scale coupling, from event horizon scales to megaparsec scales, makes black holes some of the most important objects in shaping cosmic structure. Near TON 618, time itself warps. This is not metaphor or analogy, but literal description of physical reality. General relativity predicts, and countless experiments confirm, that time flows at different rates in different gravitational fields. Near massive objects, time slows. The effect is subtle on Earth's surface, a few microseconds per day difference between sea level and mountaintops. But near black holes, time dilation becomes extreme. To understand gravitational time dilation, we must revisit special relativity first. Einstein's 1905 theory revealed that moving clocks tick slowly relative to stationary ones. If you board a spacecraft and accelerate to high velocity while your twin remains on Earth, less time passes for you than for your twin. Return after what feels like 1 year at 99% light speed, and you find over 7 years have passed on Earth. This is time dilation, a real physical effect confirmed in countless experiments. General relativity extends this insight to gravity. Strong gravitational fields slow time just as high velocities do. The physical reason lies in the equivalence principle, the observation that acceleration and gravity produce identical local effects. If time slows for accelerated observers and gravity is equivalent to acceleration, then time must slow in gravitational fields. The mathematical description is precise. A clock in a gravitational potential runs slower by a factor of R²'s 1 minus 2 gmRc², compared to a clock infinitely far from the mass m. Here g is the gravitational constant, r is the distance from the center, and c is light speed. For weak fields like Earth's surface, this factor is extremely close to 1. The correction is tiny, about 1 part in a billion, but near black holes, the factor becomes significant. Approaching the event horizon, where 2 gmRcQ2 approaches 1, the square root approaches 0. Time slows dramatically. Right at the event horizon, where 2 gms/RCCQ3 equals exactly 1, time appears to stop entirely from the perspective of a distant observer. This creates the famous frozen star appearance. Watch an object fall toward a black hole, and you see it slow down as it approaches the horizon. The object appears to take infinite time to reach the horizon, its motion asymptotically approaching, but never quite reaching that boundary. The light from the object becomes increasingly red-shifted, shifted toward longer wavelengths and lower frequencies. Eventually, the wavelength becomes so long and the signal so dim that the object fades from view, but you never actually see it cross. From the falling object's perspective, nothing special happens at the horizon. It crosses smoothly in finite proper time. Time, as measured by a clock falling with the object, ticks normally, but the relationship between this proper time and coordinate time measured by distant observers becomes stretched. What feels like 1 second to the falling observer corresponds to minutes, hours, years, centuries to someone watching from far away. Near TON 618's event horizon, these effects are calculable. Let's consider an observer stationed at twice the event horizon radius at 2,600 AUP from the center. At this location, the time dilation factor is crossed 1 minus 1/2 equals 1/2, approximately equal to 0.707. Time flows at roughly 71% the rate compared to a clock infinitely far away. If you spent 1 year at this location, about 1.4 years would pass for someone far from the black hole. This might not sound dramatic, but consider closer approach. At a radius of 1.5 times the event horizon, 1950 AU, the time dilation factor becomes right as 2/3, approximately equal to 0.577. Time flows at 58% the distant rate. 1 year here equals about 1.7 years far away. At 1.1 times the event horizon, just 130 ATO outside the point of no return, the factor becomes records 1 minus 1 over 1. 1 approximately equal to 0.316. Time flows at only 32% the distant rate. 1 year here corresponds to over 3 years far away. At 1.01 times the horizon radius, just 13 AUO outside, the factor is Reculers 1 minus 1 slash 1.01, approximately equal to 0.1. Time flows at 10% the distant rate. 1 year here equals 10 years far away. This progression continues. At 1.001 times the horizon, time flows at roughly 3% the distant rate. At 1.0001 times, less than 1%, you could hover just above the event horizon and watch centuries pass in the distant universe during what feels like minutes to you. The entire future history of the universe could theoretically unfold before your eyes if you could maintain position near the horizon and somehow observe distant events. This effect has been portrayed in science fiction, most famously in the film Interstellar, where the protagonist spends hours on a planet near a massive black hole and returns to find decades have passed for his colleagues. While that specific scenario involved a fictional black hole, the physics is sound. Time really does behave this way, near extreme gravity. The twin paradox of special relativity gets amplified to cosmic proportions. Imagine identical twins. One remains far from TON 618, on a distant planet in a normal galaxy. The other journeys to TON 618 and hovers at 1.1 times the event horizon radius for what feels like 1 year, then returns. Upon reunion, the traveling twin has aged 1 year plus travel time. The stay-at-home twin has aged over 3 years plus travel time. The difference is real, not apparent. If the stay-at-home twin was 30 years old when the traveler left and is now 34, the traveler is only 32. Biologically, psychologically, by every measure, less time has passed for them. This becomes more extreme closer to the horizon. Hover at 1.01 times the horizon for 1 year, and 10 years pass elsewhere. Hover at 1.001 times for 1 year, and over 30 years pass. The mathematics is unambiguous. However, practical challenges emerge. Hovering near the event horizon requires constant acceleration to counteract the enormous gravitational pull. The acceleration needed grows extreme as you approach the horizon. At the horizon itself, infinite acceleration would be required, which is obviously impossible. Even approaching very close demands accelerations far exceeding anything achievable with known propulsion. Moreover, if you are not hovering but instead in free fall, you do not experience time dilation relative to your own reference frame. You always measure your clock ticking normally. The dilation only manifests when comparing to clocks at different gravitational potentials. An observer in free fall from far away who plunges across the horizon experiences only finite proper time, hours or days, for TON 618. From beginning the fall to reaching the singularity, with no awareness of infinite time passing elsewhere. Gravitational time dilation also affects light. Photons climbing out of a gravitational well lose energy, manifesting as gravitational redshift. Light emitted from near the event horizon is dramatically redshifted by the time it reaches distant observers. A photon emitted with visible wavelength near the horizon might arrive as an infrared or radio photon after climbing out of the gravitational well. This redshift combines with Doppler shifts from material motion in the accretion disk. Disentangling these effects requires careful modeling, but provides information about conditions near the event horizon. The innermost stable circular orbit, where emission peaks, has characteristic gravitational redshift that depends on black hole spin. By measuring this redshift through spectral line profiles, astronomers can constrain spin. Time dilation also affects the appearance of orbiting material. Gas orbiting in the accretion disk near the event horizon experiences significant time dilation. Processes that appear to take a certain amount of proper time in the gas's reference frame appear much longer to distant observers. If an instability in the disk produces a flare lasting 1 hour, as measured in the disk's frame, that flare might appear to last several hours to days, for distant observers depending on the disk radius and time dilation factor. This time dilation can smooth out rapid variability. Intrinsically brief events get stretched in observed duration. However, for actively accreting systems like TON 618, variability on multiple timescales is observed, from hours to months. Disentangling intrinsic variability timescales from time dilation effects requires modeling. Another consequence involves communication. Suppose you could establish a communication link between an observer near the event horizon and one far away. Messages sent outward from near the horizon would be received at the distant location much later than the sender might expect. A signal sent every hour, according to the near-horizon clock, might be received every several hours according to the distant clock. The message content would also be redshifted, affecting transmission fidelity. Conversely, messages sent inward from far away would be received blue-shifted and time-compressed at the near-horizon location. A signal sent every hour by the distant observer might be received every few minutes by the near-horizon observer. This asymmetry is a direct consequence of gravitational time dilation. These effects are not science fiction or theoretical curiosities. They are real properties of space-time geometry near massive objects, confirmed by decades of experimental tests. GPS satellites must account for time dilation both from their orbital velocity and from being in Earth's weaker gravitational field compared to the surface. Without these corrections, GPS would accumulate errors of kilometers per day. If we can measure these tiny effects from Earth's modest gravity, the extreme effects near black holes are certainly real. For TON 618, these time dilation effects create a peculiar situation. We observe ancient light from 10.8 billion years ago. At that time, material near the event horizon experienced extreme time dilation. Events near the horizon occurred in slow motion from the perspective of distant observers. Yet we see this entire scene now, frozen in time by the finite light travel speed. We are watching a slow-motion movie of extreme gravity from billions of years ago. If an observer could somehow have remained near TON 618's horizon since then, experiencing maximum time dilation, vastly less proper time would have passed for them than the 10.8 billion years that have elapsed in most of the universe. While galaxies formed and evolved, stars lived and died, and civilizations potentially arose and fell across the cosmos, an observer near the horizon would have experienced only a fraction of that duration. This raises profound questions. Could someone theoretically use black holes for time travel, at least forward in time? By approaching a black hole closely, experiencing extreme time dilation, then returning to normal space, you would have traveled into the future of the external universe. While you aged a year, centuries might have passed elsewhere. However, practical challenges are immense. Surviving the tidal forces, generating sufficient thrust to hover or orbit near the horizon, and returning safely all pose essentially insurmountable engineering problems with known physics. Nature provides the mechanism for time travel to the future via relativity, but exploiting it requires capabilities far beyond current technology. Yet the principle remains. Time is not absolute. It flows at different rates in different circumstances. Near Ton 618, time behaves in ways utterly foreign to everyday experience. Understanding this deepens our appreciation of relativity's radical implications and of how extreme environments teach us that our intuitions about space, time, and causality are local approximations, valid only in the gentle gravitational fields and low velocities of everyday life. The concept of a habitable zone, that Goldilocks region around a star, where temperatures allow liquid water to exist on planetary surfaces, is fundamental to astrobiology. Around our Sun, this zone extends roughly from Venus's orbit to Mars's orbit, a band where Earth sits comfortably. Planets too close are scorched. Planets too far freeze. But the zone itself, defined by distance and stellar luminosity, permits conditions conducive to life as we know it. Could such a zone exist around TON 618? The question seems absurd at first consideration. This is a black hole, not a star. It generates no fusion energy to warm orbiting planets. Its environment is characterized by extreme gravity, intense radiation, and violent instabilities. Yet TON 618 does emit vast amounts of energy, 140 trillion times the Sun's luminosity. If energy output defines a habitable zone, perhaps one exists here as well. Let us calculate. The habitable zone distance depends on luminosity. More luminous objects have habitable zones farther out. For the Sun, at 3.8 times 10 WK watts, the habitable zone sits at roughly 1 AU. Scale this by the square root of luminosity ratio. TON 618 at 4 times 10 watts is about 10 times more luminous. The square root is roughly 10 degrees. The habitable zone would sit about 10 million AUA away. 10 million astronomical units equals approximately 0.16 light-years, or about 1.5 trillion kilometers. This is about 1/30th the distance to Proxima Centauri, our nearest stellar neighbor. At this distance, TON 618 would appear as a brilliant point, far brighter than any star or planet in our sky, but still a point, not a resolved disk. A planet at this distance would receive similar total energy flux as Earth receives from the Sun. Purely from energy balance, temperatures might permit liquid water. The calculation is straightforward, thermodynamics. But this superficial analysis ignores multiple catastrophic problems that make life impossible. First, the radiation spectrum is utterly hostile. The Sun emits primarily visible light with some infrared and ultraviolet. This spectrum is relatively benign. Earth's atmosphere blocks the most harmful ultraviolet. What reaches the surface drives photosynthesis and warms the planet without immediately sterilizing it. TON 618's emission includes intense ultraviolet and X-ray radiation. The accretion disk's innermost regions, heated to billions of degrees, produce hard X-rays and gamma rays. These photons carry enough energy to ionize atoms deep within matter, breaking chemical bonds, destroying complex molecules, and producing lethal radiation doses. Even at the calculated habitable zone distance of 0.16 light-years, X-ray and ultraviolet flux would be intense. Any planet would be bathed in radiation far exceeding levels that biological molecules can tolerate. DNA would be shredded, proteins denatured, cell membranes disrupted. No known form of life could survive on an unshielded surface. Perhaps life could hide underground or beneath thick ice layers. On Earth, extremophile bacteria live kilometers underground, shielded from surface conditions. Might similar strategies work near TON 618? Possibly, but other problems remain. Second, the environment is violently unstable. TON 618 is a quasar, actively accreting enormous quantities of matter. This accretion is not smooth and steady, but chaotic and variable. The disk experiences instabilities magnetic reconnection events, and turbulent fluctuations. Luminosity varies on timescales from hours to months. A planet in the habitable zone would experience dramatic swings in received energy. During luminosity peaks, temperatures might soar, vaporizing oceans. During dips, temperatures might plummet, freezing everything. These variations would occur too rapidly for planetary systems to equilibrate thermally. The surface would experience wild swings incompatible with stable liquid water. Moreover, quasar activity is episodic on longer timescales. TON 618 shines brilliantly now, but this phase will not last forever. Within tens of millions of years, perhaps 100 million at most, the gas supply will be exhausted. The quasar will fade, luminosity will drop by factors of thousands or millions. The habitable zone will collapse inward, moving from 0.16 light-years to perhaps 1,000 AUS or less, if the black hole continues modest accretion, or vanishing entirely if accretion ceases completely. Any hypothetical life that evolved during the bright quasar phase would face extinction when the quasar fades. The time scale for fading, tens of millions of years, sounds long but is short for biological evolution. On Earth, complex multicellular life took billions of years to evolve. Intelligence required even longer. Evolution cannot adapt quickly enough to compensate for luminosity changes of factors of thousands occurring over millions of years. Third, stellar systems are unlikely to form or remain stable in this environment. Planet formation requires protoplanetary disks, rotating disks of gas and dust, around young stars where particles collide, stick together, and gradually build planets over millions of years. Such disks are delicate structures, sensitive to disruption. Near TON 618, the tidal forces at 0.16 light-years are not negligible. While not strong enough to immediately tear apart a planet, they complicate formation. The intense radiation field would heat and photoevaporate protoplanetary disk material, potentially preventing planet formation entirely. Stellar winds and jets, if present, would blow away disk material. Even if planets somehow formed, orbital stability is questionable. At 0.16 light-years from a 66 billion solar mass object, orbital velocities are modest, perhaps a few kilometers per second. Orbital periods are long, hundreds of thousands to millions of years. During such long periods, gravitational perturbations from passing stars or gas clouds could destabilize orbits, ejecting planets or sending them on highly eccentric trajectories. Fourth, the entire region is suffused with ionized gas from the accretion disk and any outflows. Even at large distances, the quasar's intense radiation ionizes the surrounding medium out to many light-years. A planet in this environment would experience constant bombardment by high-energy particles and ionized plasma. This cosmic sandblasting would erode atmospheres, strip away protective magnetic fields, and further sterilize surfaces. Fifth, consider the host galaxy context. TON 618 sits at the center of a galaxy undergoing intense star formation and possibly merger activity. The galactic environment is chaotic, with gas flows, stellar winds from massive stars, supernova explosions, and possibly interactions with other galaxies. This broader context adds further instability and hazard. Supernovae within the galaxy, particularly near the galactic center where star formation is concentrated, would periodically deliver gamma-ray bursts and cosmic rays. These events might occur every few thousand to tens of thousands of years, given vigorous star formation. Each supernova could deposit lethal radiation doses on any planets, even those far from TON 618 itself. So, while one can mathematically define a distance where energy flux equals Earth's, calling it a habitable zone is deeply misleading. The spectrum is wrong. The stability is absent. The environment is hostile beyond anything life experiences on Earth. No known biochemistry could function under these conditions. Science fiction often imagines advanced civilizations harnessing black hole energy, perhaps a Dyson sphere around the accretion disk, capturing radiated energy for power generation, or perhaps energy extraction from the black hole's rotation through the Penrose process or similar mechanisms. These scenarios push technological capabilities to extremes, but are not fundamentally prohibited by physics. However, such megastructures would not provide habitable environments in the conventional sense. They would be artificial habitats, heavily shielded, carefully engineered to maintain stable conditions despite the chaotic surroundings. This is engineering on a scale utterly beyond current capabilities, requiring materials that can withstand extreme radiation, tidal stresses, and temperature variations. It is perhaps conceivable in principle for a sufficiently advanced civilization, but remains firmly in the realm of speculation. Moreover, why would a civilization choose this location? Energy is abundant elsewhere. Without the extreme hazards, stars provide stable, predictable energy outputs for billions of years. Solar panels in normal stellar systems can capture energy efficiently without requiring megastructure engineering near black holes. The primary motivation for approaching TON 618 would be research, not habitation. To study physics in extreme conditions, to test general relativity, to probe the event horizon's properties, but not to establish colonies or permanent settlements. Could life exist elsewhere in TON 618's host galaxy, far from the black hole and quasar, but within the same gravitational system? Possibly. If the galaxy contains stable regions far from the violent center, perhaps in spiral arms where stars form from relatively unperturbed gas clouds, those regions might host planets with conditions amenable to life. The galaxy, after all, contains hundreds of billions of stars. Many could have planetary systems. Some fraction might occupy true habitable zones around stable stars. But this would be life in the galaxy, not life around TON 618 specifically. The black hole's influence at distances of thousands or tens of thousands of light-years diminishes to negligibility for planetary habitability. At such distances, TON 618 is simply the gravitational anchor holding the galaxy together, with no direct impact on whether individual planets can support life. The answer, then, is clear. TON 618 cannot support a habitable zone in any meaningful sense. The radiation is lethal. The environment is unstable. The timescales are incompatible with biological evolution. Life as we know it, based on liquid water, complex organic chemistry, and stable energy inputs, cannot exist near this object. It is a monument to extreme physics, not a cradle for biology. This conclusion extends to most actively accreting supermassive black holes. Quasars are inhospitable. They are too violent, too variable, too hazardous. Only after the quasar phase ends, when the black hole settles into dormancy and the host galaxy quiets, might stable habitable zones exist elsewhere in the galaxy. But by then, the black hole itself has become irrelevant to habitability, simply a massive gravitational presence around which the galaxy rotates. TON 618, with its 66 billion solar masses, ranks among the most massive black holes ever discovered. But it is not unique. A handful of other ultramassive candidates have been identified, each pushing the boundaries of what black holes can become. Comparing these giants reveals patterns in black hole growth and hints at potential upper limits imposed by physics. At the opposite end of the mass spectrum sits Sagittarius A, the supermassive black hole at our Milky Way's center. With approximately 4 million solar masses, Sagittarius A is modest by supermassive standards. Its event horizon radius is about 12 million kilometers, roughly 0.08 AU. You could fit 16,500 copies of Sagittarius A inside TON 618 by mass. Despite its relative small size, Sagittarius A is scientifically invaluable because of proximity. At only 26,000 light-years from Earth, It is the nearest supermassive black hole. We can observe stars orbiting it directly, tracking their motions over decades. One star, S2, completes an orbit every 16 years. At closest approach, it passes within 128 IU of the black hole, reaching velocities of 3% of light speed. These observations provided some of the most direct evidence for supermassive black holes and allowed precise mass measurements. Sagittarius A is also remarkably quiet. It accretes very little, shining at only a tiny fraction of its Eddington luminosity. Occasional flares occur when material falls in, but most of the time, it is essentially dormant. This quiescence is typical for local universe black holes. The quasar era ended billions of years ago. Most supermassive black holes now sit starved of fuel, having consumed nearby gas and entering long dormancy. Moving to more massive examples, M87, the black hole at the center of the giant elliptical galaxy Messier 87, contains approximately 6.5 billion solar masses. M87 sits about 55 million light-years away in the Virgo cluster. This black hole achieved fame in 2019 when the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow and surrounding photon ring. The image showed a dark central region surrounded by a bright ring of emission from the accretion disk. The shadow's size, about 40 micro-arcseconds across, as viewed from Earth, matches predictions from general relativity for a black hole of M87's mass. This observation provided direct visual confirmation of event horizon existence and tested general relativity in strong field conditions. M87 produces a prominent jet, clearly visible in radio observations extending thousands of light-years from the galaxy center. This jet deposits enormous energy into the surrounding intracluster medium, creating cavities visible in X-ray images. The jet's power and structure have been studied extensively, providing insights into jet formation mechanisms. At 6.5 billion solar masses, M87 is about 10 times less massive than TON 618. Its event horizon radius is proportionally smaller, roughly 130 ATU, compared to TON 618's 1,300 ATU. Yet M87 is still enormous by most standards, far exceeding typical supermassive black holes. Phoenix A, the central black hole of the Phoenix cluster, may be even more massive than TON 618. Estimates range from 40 billion to potentially 100 billion solar masses, though large uncertainties affect these measurements. If the upper estimates are correct, Phoenix A could be the most massive black hole known, surpassing TON 618. Phoenix cluster sits about 5.7 billion light-years away, closer than TON 618, but still at cosmological distances. The cluster is remarkable for intense cooling flows, with gas in the intra-cluster medium cooling and falling toward the central galaxy at rates of thousands of solar masses per year. Much of this gas likely feeds the central black hole. Despite the vigorous feeding, Phoenix A does not shine as a bright quasar. This seems paradoxical. If it accretes thousands of solar masses per year, why is it not extraordinarily luminous? The answer may involve accretion geometry. Perhaps much of the infalling material does not form a thin radiating disk, but instead forms thick, geometrically puffed-up flows where radiation is trapped and advected inward before escaping. Such configurations can be very inefficient at producing observable radiation despite high accretion rates. Alternatively, measurement uncertainties may be significant. Black hole mass estimates for such distant objects rely on indirect methods with substantial error bars. Perhaps Phoenix A is less massive than the upper estimates suggest, reducing the apparent discrepancy between accretion rate and luminosity. Another ultramassive candidate is Holmberg 15A, residing at the center of the Holmberg 15A galaxy. itself the central galaxy of the Abell 85 galaxy cluster. This black hole has been estimated at roughly 40 billion solar masses. Like Phoenix A, it sits in a massive galaxy cluster where gas cooling flows might provide substantial fuel. Holmberg 15A is notable for another reason. The host galaxy has an extremely large core, a region where stellar density is much lower than expected. This chord structure might result from black hole mergers. When two galaxies merge and their central black holes spiral together and eventually merge, gravitational slingshot interactions with nearby stars eject those stars to larger radii, hollowing out the galactic center. The large core in Holmberg 15A suggests a merger history involving massive black holes. SDSS J0744 plus 2821 and S50014 plus 81 are quasars at high redshift with black hole mass estimates ranging from 20 billion to possibly over 100 billion solar masses for S50014 plus 81. Under some analyses, though, again with large uncertainties, these objects, like TON 618, exist at early cosmic epochs, when the universe was only a few billion years old. Their existence poses significant theoretical challenges for black hole formation and growth models. How did black holes become so massive so quickly? Even with continuous Eddington limited accretion and occasional super Eddington episodes, growing from stellar mass seeds to tens of billions of solar masses in 2 to 3 billion years requires extremely favorable conditions. This drives theoretical work on massive seed formation, direct collapse mechanisms, and optimal feeding scenarios. Comparing these giants reveals no clear winner for most massive. Measurement uncertainties overlap. Different measurement techniques yield different results. TON 618 at 66 billion solar masses, Phoenix A at potentially 100 billion, S50014 plus 81, with highly uncertain estimates. All are clearly ultramassive, all push observational and theoretical limits, but ranking them definitively is impossible with current data. What about upper limits? Is there a maximum black hole mass beyond which physics prevents further growth? Several theoretical arguments suggest limits might exist around 100 to 200 billion solar masses. First, the Eddington limit constrains growth rates. Even with continuous feeding, black holes grow exponentially with e-folding time around 50 million years. Starting from any seed mass, reaching 100 billion solar masses requires approximately 1.8 billion years of Eddington accretion. 200 billion solar masses, about 2 billion years. But the universe was only 3 to 4 billion years old during the quasar era peak. Time alone limits how massive black holes can grow. Second, feedback effects shut down growth. As black holes feed and luminosity increases, radiation pressure and jet power heat surrounding gas, eventually preventing further infall. For the most massive black holes, with the highest luminosities, feedback becomes overwhelming. Gas is blown away faster than it can be replenished. The black hole stops growing, not because fuel is exhausted, but because feedback prevents fuel from reaching it. Third, galaxy mergers become less frequent. Black hole growth through mergers depends on host galaxies colliding. In the early universe, galaxies were closer together and mergers common. But as expansion carries galaxies apart, merger rates decline. Modern universe mergers are rarer. This limits black hole growth through mergers. Fourth, total available mass in host galaxies constrains growth. Even the most massive galaxies contain only so much baryonic matter. Growing to 100 billion solar masses requires consuming a significant fraction of the galaxy's gas. At some point, there simply is not enough fuel, even if feedback were not an issue. Combining these factors, theoretical models suggest black holes larger than roughly 100 to 200 billion solar masses are unlikely, not impossible, but improbable. They would require exceptionally rare circumstances, massive seeds, continuous optimal feeding, multiple major mergers, and unusually weak feedback. We might expect a small tail of the distribution extending to such masses, but the bulk of even ultramassive black holes should remain below this range. Current observations seem consistent with this picture. The most massive black holes cluster around 10 to 100 billion solar masses. We observe none convincingly, exceeding 200 billion. This could reflect true physical limits or observational selection effects. Perhaps the most extreme examples are rarer and harder to detect. Future surveys will better constrain the high mass end of the distribution. Comparing TON 618 to others also highlights diversity. Some ultramassive black holes shine as brilliant quasars. Others are relatively quiet despite their mass. Some produce prominent jets. Others show minimal jet activity. Some sit in galaxy clusters with large gas reservoirs. Others occupy isolated galaxies. This diversity suggests multiple pathways to ultramassive status. TON 618 likely grew through some combination of massive seeds, efficient accretion, and mergers. Phoenix A might emphasize different processes, perhaps sustained feeding from cooling flows compensating for lower initial mass. M87 achieved its large mass through growth in a massive host galaxy over billions of years, now dormant after consuming available fuel. Each ultramassive black hole tells part of the story of structure formation and galaxy evolution. Each represents an extreme outcome of gravitational assembly. Collectively, they map the boundaries of what black holes can become in our universe. Observing an object 10.8 billion light-years away poses extraordinary challenges. TON 618 appears as a single point of light, even in the most powerful telescopes, its angular size far below resolution limits. We cannot see structure directly. We cannot image the accretion disk or event horizon. Yet through clever techniques combining multiple wavelengths, spectroscopy, and careful analysis, astronomers extract remarkable information about this distant monster. The primary tool is spectroscopy, the analysis of light split into component wavelengths. When TON 618's light enters a telescope and passes through a spectrograph, it is dispersed by a diffraction grating or prism into a spectrum showing intensity at each wavelength. This spectrum contains information about composition, temperature, velocity, and ionization state of emitting material. The spectrum shows a continuum, emission rising and falling smoothly across wavelengths, representing thermal emission from the accretion disk and non-thermal processes like synchrotron radiation. Superimposed on this continuum are emission lines, bright features at specific wavelengths where particular atomic transitions produce enhanced emission. For TON 618, prominent lines include hydrogen Balmer lines, oxygen lines, and others from highly ionized species. These emission lines are extraordinarily broad, smeared out over many angstroms or nanometers of wavelength. This broadening is primarily Doppler broadening from gas motion. In the broad line region, gas clouds orbit the black hole at thousands of kilometers per second. Gas moving toward us produces light blue-shifted to shorter wavelengths. Gas moving away produces light red-shifted to longer wavelengths. The combination creates broad line profiles. By measuring line widths, astronomers infer gas velocities. Typical line widths correspond to velocities of 3,000 to 10,000 kilometers per second. Using the virial theorem relating orbital velocity to central mass and orbital radius, and combining this with estimates of broadline region size from reverberation mapping or empirical relations, astronomers calculate the black hole mass. This is how the 66 billion solar mass estimate arises. The entire spectrum is also shifted as a whole toward longer wavelengths by cosmic expansion. This cosmological redshift is measured by comparing observed wavelengths to laboratory wavelengths for known atomic transitions. For TON 618, The redshift is Z equals 2.219, indicating the universe has expanded by a factor of 3.219 since the light was emitted. This redshift translates to the 10.8 billion light-year distance. Different wavelengths probe different physical processes. At radio wavelengths, typically observed with radio telescopes like the Very Large Array or ALMA, emission comes primarily from synchrotron radiation by relativistic electrons in magnetic fields. This traces jets, if present, and can reveal large-scale structure in radio lobes or extended emission regions. For TON 618, radio observations are limited by its distance and relative faintness at these wavelengths. It was not selected as a strong radio source originally, suggesting it may be radio quiet or only moderately radio loud. Deeper radio surveys with next-generation instruments might detect faint radio emission currently below detection thresholds. At infrared wavelengths, observed with space telescopes like Spitzer, WISE, or the James Webb Space Telescope, emission comes partially from the cooler outer accretion disk and from dust heated by the quasar's radiation. This infrared emission provides information about dust distribution in the host galaxy and can help measure star formation rates. JWST, with its large mirror and sensitive infrared instruments, can observe TON 618's host galaxy with unprecedented detail. By observing at wavelengths where the quasar is less dominant, JWST can potentially resolve the host galaxy's structure, measure stellar populations, and map star formation regions. These observations are ongoing or planned, promising new insights into the galaxy hosting this ultramassive black hole. At optical and ultraviolet wavelengths, observed with telescopes like Hubble Space Telescope, Keck, or the Very Large Telescope, emission comes primarily from the accretion disk itself. Different disk regions at different temperatures contribute to different wavelengths. The broad emission lines also appear prominently here, providing the primary mass measurement tool. Optical spectroscopy is particularly powerful. Modern spectrographs can achieve spectral resolution of a few angstroms or better over wide wavelength ranges. This allows detailed line profile analysis, measuring not just widths, but also subtle asymmetries that might indicate inflows or outflows, and multiple line components that might trace different gas populations. At X-ray wavelengths, observed with space telescopes like Chandra or XMM Newton, emission comes from the hottest innermost disk regions and from Compton scattering processes where high-energy electrons collide with photons, boosting their energies. X-ray observations probe conditions closest to the event horizon, where temperatures reach billions of degrees. For very distant quasars like TON 618, X-ray observations are challenging. The signal is faint, requiring long exposure times. The X-ray spectrum is shifted by the cosmological redshift, moving characteristic emission features to different energies. Nonetheless, X-ray detections of distant quasars have been achieved, providing constraints on accretion disk properties and black hole spin. At gamma-ray wavelengths, the highest energies, observed with instruments like Fermi Gamma-Ray Space Telescope, emission might come from inverse Compton scattering in jets or from particle acceleration in magnetic reconnection events. Few quasars are detected at gamma-ray energies, and TON 618 has not been conclusively detected here, but future missions with improved sensitivity might detect it. Why can we not image TON 618 directly like the Event Horizon Telescope imaged M87 in 2019? The answer is angular resolution. The EHT achieved extraordinary resolution, approximately 20 microarcseconds, by combining radio telescopes across Earth's diameter using interferometry. This baseline of nearly 10,000 kilometers allowed resolving M87's event horizon shadow, which subtends roughly 40 microarcseconds as viewed from Earth. TON 618 is vastly more distant, over 200 times farther than M87. Even though TON 618's event horizon is physically much larger, the increased distance makes its angular size on the sky much smaller. At 10.8 billion light-years, TON 618's event horizon subtends roughly 0.1 microarcseconds, about 400 times smaller than M87's shadow. Resolving 0.1 microarcseconds would require baselines hundreds of times larger than Earth's diameter. This means space-based interferometry, with telescopes separated by significant fractions of an AU or more. Such missions have been proposed but not yet funded or built. They remain decades away. Even if we achieved the necessary resolution, detecting TON 618's shadow would be challenging. The accretion disk is extraordinarily luminous, potentially drowning out the shadow in its glare. For M87, the disk was relatively dim, allowing the shadow to stand out clearly. For TON 618 during its quasar phase, the intense emission might make shadow detection difficult, even with sufficient resolution. Future observatories will improve our view. The extremely large telescope, under construction in Chile, with a 39-meter primary mirror, will achieve much better sensitivity and resolution at optical and infrared wavelengths. It will observe distant quasars in unprecedented detail, potentially resolving host galaxy structures and studying accretion disk properties through detailed spectroscopy. The Nancy Grace Roman Space Telescope and Euclid Space Telescope will conduct wide-area surveys discovering new quasars and measuring their properties systematically. These surveys will build statistical samples of ultramassive black holes, constraining their population characteristics and testing formation theories. LISA, the Laser Interferometer Space Antenna planned for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers across the universe. If TON 618 or similar objects merge with other black holes, LISA will observe the gravitational wave signals, providing entirely new information: precise masses, spins, orbital parameters, impossible to obtain electromagnetically. Advanced X-ray observatories like Athena, planned for the 2030s, will study accretion disk physics in detail, with much higher spectral resolution than current missions. They will measure ion line profiles from the innermost disk, constraining black hole spins through relativistic effects on emission line shapes. Each new instrument adds a piece to the puzzle. We build understanding incrementally, combining observations across wavelengths and using multiple independent techniques to cross-check results. This multi-wavelength, multi-technique approach compensates for not having direct images or in-situ measurements. The reality is that for objects like TON 618, we are fundamentally limited by distance and technology. We see ancient light from billions of years ago. We observe photons that have traveled most of the universe's history to reach us. These photons carry encoded information about conditions near the event horizon, but extracting that information requires sophisticated analysis. Yet what we have learned is remarkable. From a faint blue point in archival photos, we have determined mass, distance, luminosity, accretion rate, and host galaxy properties. We have tested general relativity, constrained formation mechanisms, and probed cosmic history. This is the power of modern astrophysics, to reach across cosmic distances and cosmic time, extracting deep insights from the faintest signals. TON 618 does not exist in isolation. It sits at the center of a galaxy, gravitationally bound to hundreds of billions of stars, vast quantities of gas and dust, and dark matter halos. The black hole and galaxy influence each other through complex feedback loops that regulate star formation, gas content, and long-term evolution. Understanding this coevolution is crucial for comprehending how galaxies develop their observed properties. The story begins with an empirical discovery. In the late 1990s and early 2000s, Astronomers noticed tight correlations between supermassive black hole masses and host galaxy properties. Specifically, black hole mass correlates strongly with the stellar mass and velocity dispersion of the galactic bulge, the central concentration of stars in disk galaxies, or the main body of elliptical galaxies. The correlation with velocity dispersion is particularly tight. Measure how fast stars move randomly in the bulge, their velocity dispersion, and you can predict the central black hole mass with remarkable accuracy. The relationship is roughly m_bh, approximately equal to 10 m time pi, sigma 200 kilometers sols, where sigma is the velocity dispersion. Double the velocity dispersion, and the black hole mass increases by a factor of 16. This correlation is not obvious a priori. The black hole contains perhaps 0.1% to 0.5% of the bulge mass. It gravitationally dominates only the inner few light years, or tens of light years. The bulge extends for thousands of light years. How do these vastly different scales coordinate their properties? The answer involves feedback. As black holes grow through accretion, they produce enormous energy output. This energy couples to surrounding gas, heating it and potentially driving it away. The same processes also affect star formation, because star formation requires cool, dense gas. Heat, or remove that gas, and star formation ceases. The mechanisms operate through several channels. Radiative feedback involves radiation pressure and heating. Photons from the accretion disk carry momentum. When absorbed by gas, they transfer that momentum, accelerating the gas outward. For luminous quasars near Eddington luminosity, radiation pressure can drive winds at thousands of kilometers per second. Additionally, ultraviolet and X-ray photons ionize and heat gas. Photoionization creates hot, ionized plasma. Photoelectric heating from dust grains adds thermal energy. Compton heating, where X-rays scatter off electrons and transfer energy, heats gas to millions of degrees. Hot gas has high thermal pressure, resisting gravitational compression. This prevents collapse into dense clumps where stars form. Mechanical feedback involves jets and winds. Jets, if present, deposit kinetic energy and momentum into the surrounding medium. They plow through gas, creating shock waves that heat material and excavate cavities. Observations of nearby galaxy clusters show enormous radio lobes carved by jets, with volumes reaching hundreds of cubic kiloparsecs and requiring 10 to 10 ergs of energy to inflate. Winds, driven by radiation pressure or magnetic processes, also transport energy. These outflows can reach velocities of thousands of kilometers per second, carrying gas away from the galaxy entirely if velocities exceed the escape velocity. Alternatively, winds might not fully escape but mix with the surrounding medium, depositing energy and entropy that affects gas properties over large volumes. The feedback process creates self-regulation. As a black hole feeds and grows, energy output increases. Eventually, feedback becomes strong enough to disrupt the gas supply. Infall stops, accretion declines, luminosity drops. Feedback weakens. This allows gas to cool and potentially fall back in, reigniting accretion. The cycle might repeat episodically. Over long time scales, this self-regulation produces a roughly constant ratio between black hole mass and bulge mass. Black holes grow until feedback shuts them down. More massive bulges have deeper gravitational potential wells, requiring more feedback energy to expel or heat gas. This allows their central black holes to grow larger before feedback becomes effective, hence the correlation. For TOM 618 specifically, with 66 billion solar masses, the correlation predicts a bulge mass of order 10 times square to 10 solar masses, comparable to or exceeding the Milky Way's total stellar mass. This suggests the host galaxy is extremely massive, likely a giant elliptical, or the progenitor of one. The intense quasar luminosity means feedback is currently operating at full strength. Ton 618's radiation heats gas throughout the host galaxy. If jets exist, they inject additional energy. Star formation might be suppressed in regions affected by this feedback. Or conversely, shock waves from jets might trigger localized star formation in compressed gas. The host galaxy is probably undergoing a starburst, forming stars at rates perhaps hundreds to thousands of times the Milky Way's current rate. This vigorous star formation and vigorous black hole feeding both trace abundant gas supplies. They are likely triggered by the same event, perhaps a major galaxy merger that funneled gas toward the center, simultaneously feeding the black hole and triggering star formation in compressed gas. Over time, both processes will exhaust the gas. Star formation will convert gas into stars. Supernova, from massive stars, will heat and expel some gas. The quasar will either consume gas through accretion or expel it through feedback. Within tens to perhaps 100 million years, both the starburst and quasar will fade. The galaxy will settle into a quiescent state. Billions of years after the epoch we observe, the host galaxy has likely evolved into a massive, quiescent elliptical. Star formation has ceased. The stellar population is old and red, dominated by long-lived low-mass stars. The black hole sits dormant, no longer accreting significantly. The galaxy resembles modern-day giant ellipticals found in galaxy cluster centers, old, red, massive, and inactive. This evolutionary sequence from gas-rich star-forming systems to quiescent ellipticals appears common for massive galaxies. Observations across cosmic time show that the most massive galaxies transitioned from active to quiescent earlier in cosmic history. By 8 to 10 billion years ago, many giant ellipticals had already formed and ceased star formation. They have evolved passively since then, with minimal change. TON 618, observed at 3.2 billion years after the Big Bang, sits early in this sequence. It represents a massive galaxy in formation, actively building stellar mass and black hole mass. The feedback processes we infer, theoretically, are operating in real time, shaping the galaxy's future evolution. The connection between black hole growth and galaxy evolution extends beyond individual galaxies. On cosmic scales, the decline in quasar activity from 2 to 4 billion years after the Big Bang to the present correlates with the decline in cosmic star formation rate. The universe as a whole formed stars most vigorously during the quasar era. As quasar activity declined, so did star formation. This likely reflects shared underlying causes. Both quasar fueling and star formation require abundant cold gas. In the early universe, gas fractions were high. Mergers were common, triggering both black hole feeding and star formation. As the universe aged, gas was consumed or expelled. Mergers became rarer, and both processes declined. Additionally, feedback from quasars and star formation, through supernova and stellar winds, may have collectively heated and expelled gas from galaxies, contributing to the decline in both phenomena. This represents a complex interplay, where galaxies, black holes, and star formation co-evolve through interconnected physical processes. Understanding these processes matters for explaining observed galaxy properties. Without feedback, theoretical models predict massive galaxies would continue forming stars at high rates, growing far larger than observed. The most massive galaxies would contain far more stars than they do. The fact that massive galaxies are typically quiescent suggests efficient feedback mechanisms shut down growth. Supermassive black holes, despite their tiny masses relative to galaxies, play outsized roles in this regulation. Their energy output, when feeding actively, can heat or expel gas from entire galaxies. This makes them crucial regulators of galaxy evolution, particularly for the most massive systems. TON 618 exemplifies this process. Its current vigorous accretion and enormous energy output will likely shape the host galaxy's future. Gas will be heated or expelled. Star formation will be regulated. The final state, billions of years later, will reflect the cumulative effects of this black hole feedback operating during the galaxy's youth. Thought experiments often illuminate physics by isolating specific effects and considering extreme scenarios. Let us imagine, purely hypothetically, that TON 618 suddenly replaced our Sun. What would happen? The sequence of events would be catastrophic, rapid, and utterly devastating. But the specific timeline and mechanisms reveal interesting physics. First, the gravitational effects. TON 618 contains 66 billion solar masses, about 16,500 times our Sun's mass. Gravitational force is proportional to mass, so immediately every planet would experience 16,500 times stronger gravitational pull toward the center. Earth orbits at 1 AU, taking 1 year to complete an orbit at about 30 kilometers per second. Place TON 618 at the center, and Earth's orbital velocity becomes insufficient to maintain stable orbit. The required orbital velocity increases with the square root of central mass. For TON 618, Earth would need to orbit at approximately square root of 16,500, approximately equal to 128 times faster, roughly 3,900 kilometers per second, to remain at 1 AU. Earth is moving at only 30 kilometers per s. This is catastrophically insufficient. Earth would immediately begin falling inward, no longer supported by orbital motion against the enhanced gravity. The fall would accelerate rapidly. Using simple gravitational dynamics, Earth would reach the black hole's vicinity within hours to days, not the months or years one might naively expect. The other planets experience similar fates. Mercury, Venus, Mars, all inner planets begin falling inward immediately. The outer planets, Jupiter, Saturn, Uranus, Neptune, also fall inward, though they start farther out and take slightly longer. But slightly longer means days instead of hours, not a significant reprieve. As planets fall inward, tidal forces intensify. Initially, tidal forces across planetary diameters are modest, but as distance decreases, forces grow as the inverse cube of distance. Within hours, as Earth falls to perhaps 0.1 AUH or closer, tidal forces become extreme. Earth's near side, closer to the black hole, experiences stronger gravitational pull than the far side. The difference exceeds the forces holding Earth together. The planet begins deforming, elongating toward the black hole. Earthquakes shake the surface as tectonic plates shift. Volcanic eruptions increase as internal stresses mount. Within hours to a day, Earth ruptures. The crust breaks apart. Magma erupts from widening fractures. The planet disintegrates into chunks, still falling inward but no longer a coherent sphere. These chunks continue falling, heating from compression and tidal friction. Some evaporate into gas clouds, others become part of a rapidly forming accretion disk. What about the Sun itself? If TON 618 replaced the Sun, where did the Sun go? Let us imagine it remains in the system, orbiting TON 618 at its original 1 AU location. Like Earth, the Sun would fall inward, unable to maintain orbit at original velocity. The Sun contains far more mass than Earth, roughly 333,000 Earth masses, but this provides no protection. It falls inward just as rapidly, governed by the same gravitational dynamics. As it approaches TON 618, tidal forces tear it apart. The Sun disrupts within hours to days, depending on exact trajectory. The process of tidal disruption creates spectacular displays. As the Sun stretches and deforms, outer layers are pulled away first. A long stream of stellar material spirals toward the black hole, heating through friction in the forming accretion disk. This generates enormous energy, potentially creating a temporary quasar-like flare, visible across intergalactic distances. Meanwhile, life on Earth has already ended. Even before Earth disintegrates, survival becomes impossible. If we imagine humans somehow protected from immediate gravitational effects, perhaps aboard spacecraft with powerful engines, other factors intervene. First, darkness and cold. The sun, our primary energy source, is being destroyed or has fallen into the black hole. Earth's surface receives no sunlight. Temperatures plummet. Within hours, surface temperatures drop below freezing. Within days, they approach the temperature of deep space, perhaps minus 200 degrees or minus 250 degrees Celsius. Oceans freeze solid. The atmosphere begins condensing and precipitating as snow. Second, radiation. Tom 618, if still actively accreting, emits intense radiation. If material from the destroyed sun and planets forms an accretion disk, additional intense radiation is generated. Earth would be bathed in X-rays and ultraviolet, far exceeding lethal doses. Any survivors on the surface would be sterilized within hours. Third, material bombardment. Debris from disrupted planets and the sun forms a chaotic cloud, with collisions common. Earth, even if temporarily intact, would experience relentless impacts from asteroid to moon-sized fragments, each impact delivering energy far exceeding any natural disaster in history. The timeline from TON 618's appearance to Earth's complete destruction is approximately 12 to 24 hours, less than a single day. One moment, solar system existing normally. Next moment, utter annihilation. No evacuation is possible. No defense exists. The scenario is absolute extinction. What emerges afterward? The solar system's material. 8 planets, hundreds of moons, billions of asteroids and comets. The sun itself totals approximately 1.001 solar masses, overwhelmingly dominated by the sun. This entire mass is captured by TON 618, quickly accreting or forming debris disks. Within days to weeks, much of the material settles into an accretion disk around TON 618. The disk is vastly smaller and less massive than the disks that typically feed quasars from galactic-scale gas supplies. It represents only a trivial addition to TON 618's 66 billion solar masses, increasing the black hole's mass by roughly 0.0000002%. This accretion produces a luminosity surge, perhaps comparable to a stellar tidal disruption event. For weeks to months, TON 618 would shine brighter as the solar system's material falls in. Then the fuel is exhausted, the flare fades. TON 618 returns to dormancy or continues feeding from other sources if any exist. What about forming new structures? Could planets form around TON 618 like planets form around stars? In principle, yes. If a stable disk of gas and dust forms and persists for millions of years, planets might coalesce through the same accretion processes that form planets around stars. However, conditions differ dramatically. The timescales for accretion disk evolution around black holes are much shorter than for protoplanetary disks around young stars. Material spirals inward rapidly, crossing the event horizon within thousands to tens of thousands of years, rather than remaining in stable orbits for millions of years. This makes planet formation difficult. Additionally, the radiation environment is hostile. Intense X-ray and ultraviolet emission from the accretion disk would photo-evaporate solid particles before they could grow into planets. The disk would be too hot and ionized for dust grains to stick together and grow. So, while the disk might form from the solar system's material, it would not produce new planets. It would simply feed the black hole temporarily before dissipating. This thought experiment illustrates the vast gulf between stellar masses and ultramassive black hole masses. TON 618 could consume thousands of solar systems without noticeable mass gain. It operates on scales so enormous that entire planetary systems are negligible perturbations. It also highlights black hole lethality, not from the event horizon itself, but from gravitational dominance at large distances. TON 618's event horizon sits at 1,300 AU, far beyond planetary orbits, but its gravitational influence extends vastly farther. Place it at the solar system's center, and its gravity overwhelms everything within hundreds or thousands of AU, destroying all structures. This is why black holes are fundamentally different from stars, despite sometimes playing similar roles as gravitational anchors for systems. Stars support stable planetary systems through relatively gentle gravity and steady energy output. Black holes, especially ultramassive ones, create unstable hostile environments where planets cannot survive.